In 1968, a quiet mathematical accident cracked physics open, and the equations started to sing, not metaphorically, but literally, as if every particle were a note played by a hidden vibrating string beneath atoms and galaxies. If that's true, what is spacetime really made of, and are we about to discover that reality has an edge we can't cross? Look up long enough, and the universe stops feeling like a place, and starts feeling like a rule. Somewhere between what we can measure and what we can only infer, a boundary begins to take shape. Tonight, we follow that boundary as it shifts from the farthest galaxies to the smallest meaningful distance. Cosmology tells us the sky is not a window onto everything, but a record of what light had time to deliver. In that record, patterns survive. Faint temperature ripples, stretched wavelengths, and the slow erasure of distant structures by expansion. Yet the deeper we look, the more the universe seems to ration access, as if observation itself comes with a price. Physics has two rulebooks that rarely fail, and almost never agree when it matters most. Quantum theory describes a world of probabilities and interference, where fields fluctuate even in perfect vacuum. Relativity describes a world of geometry and causality, where gravity is not a force but the shape of spacetime. Each is breathtakingly precise, until black holes and beginnings force them into the same sentence. To unite them, we will need more than a new equation. We may need a new idea of what distance means. When we try to probe ever smaller scales, energy crowds into tiny regions, and nature answers with horizons. The attempt to see more can paradoxically hide more, turning a measurement into a boundary. String theory enters this story not as decoration, but as a proposal about what the universe permits. Replace point-like particles with extended objects, and violent infinities soften into smoother interactions. The mathematics begins to insist on additional directions of space, hidden not by secrecy, but by size and geometry. And as the framework deepens, it offers an unsettling possibility. That the world may resist infinite zoom, not technologically, but fundamentally. But finiteness does not always look like a wall. It can look like topology, space that loops without edges, yet holds only a limited domain. It can look like duality, where shrinking a dimension stops revealing new detail, and instead returns you to a larger description. It can look like information, where the maximum content of a region is written not in its volume, but on its boundary. We will move through these ideas slowly, with room for wonder and room for sleep. Yet every chapter tightens the same question into clearer focus. If the deepest layer of physics is built from vibrating structure, what does that demand of spacetime itself? And how far can reality be divided before division stops meaning anything? Along the way, we'll visit the strange courtroom where black holes put our principles on trial. We'll watch thermodynamics invade gravity, and we'll meet the paradox that forces modern physics to choose between cherished assumptions. We'll step into higher dimensions and brains, where geometry becomes a kind of bookkeeping, and where fundamental may depend on the perspective you choose. This is not a promise of final answers, and it is not a catalogue of fantasies. It is an exploratory journey through the best arguments we have, the sharpest limits we know, and the hints that the universe might be less like an endless stage than a structured tapestry. If there is an edge to reality, it may not be a place you can reach. It may be a principle you cannot outwit. So settle in as the visuals widen from cosmic horizons to quantum grain. Listen for the places where certainty fades into constraint, and where mathematics begins to sound like geography. By the end, the universe may feel larger than ever, precisely because it might not be infinite. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll begin with a historical clue that reshaped particle physics, then climb through clashing theories into hidden dimensions, dualities, and the limits of information. And when we reach black holes in the early universe, the question becomes unavoidable. What exactly is spacetime allowed to be? The universe looks calm from far away, but it is built from restless rules. In wide shots, galaxies seem pinned in place like lanterns, yet their light rides an expanding metric. Filaments of dark matter thread the cosmic web, long, faint bridges where clusters gather and superclusters drift. Even emptiness has structure, because vacuum is not nothing in modern physics. The observable universe is a horizon of information, limited by time, expansion, and the finite speed of light. When we look outward, we also look backward, because every photon carries a timestamp from its origin. Cosmology asks what the universe is made of, how it began, and why it has structure. Those questions feel philosophical, yet they are measured with spectra, maps, and statistical patterns. The cosmic microwave background, for example, is a cooled afterglow of the early plasma, nearly uniform but not perfectly smooth. Its tiny temperature variations are a fossil record of primordial fluctuations, the seeds of galaxies. In the quiet of deep space imagery, the universe looks finished, but it is still evolving under precise constraints. Scale is the first mystery we learn to hold without solving, because nature keeps changing its rules as we zoom. On the largest scales, gravity shapes the motion of stars and the geometry of space, bending light into arcs and lenses. General relativity treats spacetime as a dynamical fabric, where energy and momentum tell geometry how to curve. On the smallest scales, quantum mechanics governs probabilities, fields, and particles, replacing certainty with amplitudes and interference. Both theories work with brutal accuracy in their domains, and both are confirmed by experiments that leave little room for doubt. Yet they speak different languages, and the dictionary between them is incomplete. The documentary begins where those languages start to overlap, then break. We can describe a planet's orbit with smooth trajectories, and we can describe an electron with a wave function, but the early universe demands both at once. It asks for a quantum description of the very stage on which physics happens. That is where the calm panorama becomes a technical riddle, one that cannot be solved with intuition alone. Now we zoom inward, past galaxies, past stars, down to atoms. The camera dives through spiral arms, past blue nebulae and red dust lanes, then through the glare of a sun-like star. We pass the scale of planets and mountains, then the scale of cells, and then the scale where matter stops looking continuous. Atoms are mostly empty space, with electrons in quantum patterns around nuclei, and those patterns are not tiny planets. They are standing waves of a field, spread out as probability clouds, with discrete energy levels that give atoms their spectral fingerprints. Nuclei are made of protons and neutrons, themselves made of quarks and gluons. Quarks carry a kind of charge called colour, and gluons mediate the strong interaction by exchanging that colour. Unlike electromagnetism, the strong force grows stronger as quarks are pulled apart, a behaviour called confinement. This is why isolated quarks are not observed in nature, even though their effects are measured indirectly. In the mid-20th century, particle physics became a catalogue of short-lived fragments, because higher energies revealed more ways for matter to rearrange itself. Experiments smashed particles together and read the debris like weather. Bubble chambers once recorded tracks as curling strings of droplets, and later detectors replaced that with electronic layers and timing. A collision is not a simple crash, but a quantum event where probabilities interfere and then collapse into measured outcomes. The debris forms jets, resonances, and missing energy signatures that hint at invisible particles. Each new accelerator extended the microscope, not by magnifying space, but by concentrating energy into smaller effective distances. Scattering was the central tool, and it produced a central problem. When two particles collide, the outcome depends on energy, angle, and internal quantum numbers like spin, charge, and isospin. Physicists wanted formulas that matched the data and respected symmetry, because symmetry was becoming the guiding principle of the era. They also wanted the formulas to make sense, not just fit, because a good theory explains why patterns must appear. In the 1960s, the strong nuclear force looked especially stubborn, and it was not yet tamed by the later clarity of quantum chromodynamics. The strong interaction binds quarks into protons and neutrons, and binds those into nuclei, releasing the energy that powers stars. At high energies, it produces resonances, peaks that look like new particles, and the peaks were so numerous that they felt like an entire zoo. Those resonances appeared in families, aligned on patterns called Regge trajectories, where the squared mass of states rose roughly linearly with their angular momentum. The data suggested order, almost like a ladder, but the underlying mechanism was unclear. Quantum field theory methods were powerful, yet the strong force resisted simple perturbative expansion, because the coupling was not small in the relevant regime. This created a strange atmosphere in the field, part triumph, part frustration. Electromagnetism had its clean calculations, and the weak force was being organized by gauge ideas, but the strong force seemed to demand a different kind of thinking. Some researchers leaned on general principles like analyticity and unitarity, which constrain how amplitudes can behave. Others searched for symmetry structures that could classify the hadrons without revealing their internal machinery. The experimental plots kept arriving, and the theory needed a language that could keep up. In 1968, a young physicist named Gabriele Veneziano wrote down an amplitude that worked. It was not derived from a known microscopic picture, and it arrived like a clever guess guided by consistency. The formula matched key features of hadron scattering, including symmetry between channels, meaning the same expression could describe different ways the process unfolds. It encoded a property called duality, where different processes share the same description, as if the diagram you choose is a matter of perspective. It also produced an infinite tower of resonant states, spaced in a strikingly regular way, like harmonics appearing from a single rule. The Veneziano amplitude was an unexpected mathematical success, and that made it dangerous. It hinted that the strong force might be organized by a deeper principle, one that did not look like ordinary point-particle field theory. The amplitude behaved as if particles were not points, but extended objects with internal modes, because the spectrum did not end after a few states. The spectrum looked like harmonics, not isolated dots, and the regularity was hard to dismiss as coincidence. Mathematics seemed to whisper that the world had length, even at the smallest scales, and that whisper was audible in the data. Physicists began to ask what kind of object could generate that pattern. A point particle traces a world line through spacetime, and its excitations are limited to internal quantum numbers you attach by hand. An extended object traces a world sheet, a two-dimensional surface swept out as it moves, and its vibrations can form a ladder of states automatically. The Veneziano formula fit naturally with a one-dimensional object under tension, because tension sets an energy scale for oscillations. That object would be called a string, and its motion would be quantized, turning classical vibrations into discrete particles. A string is not a guitar string in space, but the analogy is useful if we keep it disciplined. It has length, tension, and allowed vibration modes, and those modes are constrained by boundary conditions and symmetry. Each mode carries energy and momentum, and in quantum physics that energy appears as mass through Einstein's relation. Different vibrational patterns would be observed as different particles, distinguished by spin and other quantum numbers. What we call an electron or a quark could be a particular note, while a heavier particle could be a higher overtone. In this view, particles are not fundamental points but manifestations of a deeper entity, and that shift changes what we mean by elementary. The string can be open with two endpoints, or closed into a loop, and the difference matters for what interactions are possible. Open strings can carry charges at their ends, which can mimic gauge interactions, the same kind that organize electromagnetism and the nuclear forces. Closed strings naturally include a vibration with the properties of a graviton, a massless spin-2 particle that couples universally. That was not the original goal, but it became the turning key. Gravity appeared not as an added feature, but as a required mode. Gravity enters the story like an uninvited guest who fits the lock. General relativity describes gravity as geometry, not as a force in space, and it has passed every precision test from Mercury's orbit to gravitational waves. Quantum mechanics describes forces as exchanges of particles in fields, and that framework underlies the standard model with astonishing accuracy. When physicists try to quantize gravity like other forces, infinities appear and refuse to cancel, because point-like interactions probe arbitrarily small distances. The problem is not technical inconvenience, but a signal that the framework is incomplete at extreme scales. At ordinary energies, the mismatch is hidden by scale, which is why daily life feels classical. The Planck length is unimaginably small, around 10⁻35 meters, where quantum fluctuations of spacetime become violent in principle. At that scale, the smooth geometry of relativity should break into something else, because the energy needed to probe it would curve spacetime dramatically. Quantum theory demands uncertainty, while relativity demands a definite causal structure, with the light cones organizing what can influence what. Push both to the extreme, and they clash, as if two consistent maps disagree about the same terrain. String theory claims the clash can be softened by extension. A point interaction happens at a single location, and that sharpness drives divergences when you integrate over all possible virtual processes. A string interaction is spread over a small area of the world sheet, blurring the ultraviolet behavior and smoothing the mathematics. The same reasoning that produced the Veneziano amplitude suggests a built-in regulator, not imposed by hand, but emerging from the object's finite size. The string length becomes a new fundamental scale, and with it comes a new way to think about what short distance even means. This matters for cosmology because the early universe was an extreme experiment, conducted once and recorded in relic light. Near the beginning, energies were high and distances were tiny, so quantum gravity effects were not optional details. If strings are fundamental, they could shape the initial conditions of spacetime, influencing which geometries are consistent and which are forbidden. They could alter how inflation begins, how singularities are avoided, or how extra fields appear, because string dynamics typically brings additional degrees of freedom. They could seed relics, defects, or patterns in primordial fluctuations, leaving subtle signatures in correlations rather than obvious objects. Cosmology is not only about what happened, but about what is possible, and that distinction is easy to miss. The universe has a history, but it also has constraints that act like laws, limiting which histories can exist at all. Those constraints decide whether time has a beginning, whether space is infinite, and whether information can be destroyed without contradiction. A quantum theory of gravity would tell us what happens at black hole horizons, where geometry and thermodynamics meet. It would also tell us what the Big Bang really means, whether it's a true origin, a transition, or a limit of description. A unified theory is the dream that these questions share one answer, and the dream has a long pedigree. In the Standard Model, forces and matter are described by quantum fields, organized by gauge symmetry and tested to many decimal places. In relativity, spacetime is dynamic, responding to energy and momentum, and the equations are geometric rather than probabilistic. Unification would place matter, forces, and geometry in one consistent framework, without patchwork rules at different scales. It would explain why there are forces at all, and why their strengths take the values we measure rather than any others. The stakes are not only philosophical, but structural, because the universe's architecture depends on microscopic rules. The distribution of galaxies depends on early fluctuations and the laws that amplified them, turning quantum noise into cosmic pattern. The stability of atoms depends on quantum rules and the particle spectrum, including the existence of light electrons and heavy nuclei. The existence of stars depends on nuclear reactions and gravity's long reach, balancing pressure against collapse for billions of years. A theory of everything would connect these layers without changing the facts, showing how the same principles echo across scale. Yet every unification attempt runs into a darker theme, the limits of reality, and limits are not always intuitive. A limit can be a smallest length, a largest density, or a maximum information content, beyond which the usual questions stop being meaningful. It can be a boundary in space-time, like a horizon, or a boundary in what can be measured, like uncertainty. It can be a statement that some questions have no operational meaning, because no experiment can distinguish the answers. Physics becomes a map of what the universe allows us to ask, and sometimes the map includes blank regions by necessity. String theory invites limits in several ways, and each limit carries a different kind of mystery. It replaces point-like probes with extended ones, making arbitrarily fine resolution impossible, because the probe itself spreads out when you try to sharpen it. It introduces extra dimensions that may be compact and hidden, curled into tiny shapes whose geometry affects particle properties. It suggests dualities where different descriptions are secretly the same physics, so that what looks like small in one picture looks like large in another. It raises the possibility that spacetime is emergent, built from deeper degrees of freedom rather than assumed from the start. If spacetime can be emergent, it might also be finite in a new sense, even if it looks continuous. The universe could be infinite in volume, yet finite in information, because horizons limit what any observer can access. It could be bounded by horizons that act like screens, turning regions of space into surfaces of encoded data. It could have a smallest meaningful unit of area, as hinted by black hole entropy, where area counts degrees of freedom. It could be discrete, not as a lattice in space, but as a limit on distinguishable states, an ultimate granularity of description. These ideas change the tone of the story because unification is a promise that comes with conditions. The promise is that the universe is intelligible, that one framework can hold the small and the large without contradiction. The condition may be that reality has an edge, a scale beyond which questions dissolve, not because we lack tools, but because the questions stop being well posed. The universe might not allow infinite detail, even in principle, the way a digital image has a maximum resolution. The deeper structure might be musical, but the music might have a highest note, set by consistency rather than choice. The 1968 clue matters because it connects beauty to constraint, and constraint is often where truth hides. A formula built to fit scattering data carried a hidden message about extension, and extension changed the ultraviolet behavior that plagued quantum gravity. That extension offered a path toward quantum gravity, and therefore toward cosmology's hardest problems, without rewriting the successes of existing physics. The clue did not prove strings are real, but it changed what a candidate theory could look like, and what kinds of answers were even imaginable. It shifted the search from particles as points to physics as patterns, where geometry and matter might be two faces of the same consistency. We are left with a central tension that will guide everything that follows. Quantum mechanics explains the small with probabilities and fields, and it thrives on superposition and uncertainty. General relativity explains the large with geometry and curvature, and it treats space-time as a smooth manifold with causal order. At the Planck scale, both demand to be true, and both cannot be complete as they stand, at least not in their familiar forms. String theory claims reconciliation, but it also multiplies possibilities and hides answers behind mathematics, because consistency can allow many solutions. The question is not only whether strings exist, but what they imply about the universe we inhabit. If the fundamental objects are strings, then space-time may be shaped by their consistency conditions, the way a melody is shaped by harmony. The number of dimensions may be fixed by quantum requirements, not by observation alone, because anomalies can break a theory unless dimensions align. The vacuum may not be unique, and the laws we see may be one region of a larger landscape, selected by history or stability. The universe may be comprehensible, yet not fully accessible, because horizons and limits can hide information by principle. This chapter began at the cosmic horizon and ended at a mathematical accident, and the arc is deliberate. The horizon reminds us that observation has limits, even before theory does, because light has only had so much time to travel. The accident reminds us that equations can reveal structure before experiments catch up, because consistency can be more predictive than intuition. Between them sits the documentary's central question about finiteness and unification, and about whether reality has a smallest meaningful scale. We will follow the clue forward, from scattering data to space-time itself, and we will keep asking what the universe refuses to let us see. Next, we move from the first whisper of strings to the deeper conflict it was trying to resolve. We push our best theories toward black holes, singularities, and the Planck scale, where calculation becomes a stress test. We watch where they break, and we ask what kind of universe requires a new language, and what kind of language can still be tested. The door opened in 1968, and we step through it carefully, listening for what the mathematics is really saying. Chapter 1 left us with a door that opened in 1968, and a problem older than that door because the mismatch was already visible in the equations. Two rulebooks describe nature with unmatched accuracy, yet they refuse to share a single page, even when we force them into the same calculation. Quantum mechanics governs the microscopic world of particles and fields, where probabilities are fundamental and interference is routine, almost mundane. General relativity governs the macroscopic world of gravity and spacetime geometry, where curvature replaces force and motion follows geometry, even for light. The central question stays in view as we move deeper, because it is both technical and philosophical in the same breath. If string theory can unify physics, what does it imply about spacetime's deepest structure, and about the meaning of location itself? Could the universe be finite in a fundamental way? Limited not by walls, but by what can be meaningfully resolved and reliably distinguished. We begin with the quantum rulebook because it is the language of matter and radiation, and it has earned that authority experimentally. In quantum mechanics, a system is described by a wave function, usually written as a complex valued object with both magnitude and phase. The magnitude relates to probability, while the phase carries the information that makes interference possible, which is why complex numbers are not optional. The wave function is not a physical wave in space, like ripples on water, even though our metaphors keep trying. It is a mathematical object that encodes probabilities for measurement outcomes, and it does so with a precision that experiments repeatedly confirm, from atoms to superconducting circuits. Visually, imagine a dim laboratory where a single electron source clicks like a metronome, steady and indifferent. A vacuum chamber hums softly, coils glow with faint heat, and a detector waits in silence for impact. On a screen, dots appear one at a time, and yet a pattern slowly emerges as minutes turn into hours. The wave function is the invisible script behind that pattern, an instruction set for how outcomes distribute when the same experiment is repeated under the same conditions. The first shock is uncertainty, which is not about clumsy instruments or human ignorance, and it does not go away with better engineering. Position and momentum cannot both be specified with arbitrary precision at once, because the theory represents them with non-commuting operators. In plain terms, the order of asking questions matters, and the mathematics refuses to pretend otherwise. The more sharply one is defined, the more the other spreads, and that trade-off is quantified by Heisenberg's uncertainty relation, dx/dp being bounded from below by h over 2. This is a structural feature of the theory, built into how states are represented and how measurements are defined, and it survives every reinterpretation. Uncertainty does not mean anything can happen, and it does not dissolve physics into chaos or mere storytelling. It means outcomes are distributed according to strict rules, with probabilities given by the Born rule, which squares amplitudes into measurable chances. The wave function evolves smoothly and deterministically between measurements, following the Schrödinger equation or its relativistic generalizations, and that evolution is unitary. Unitarity preserves total probability and keeps the bookkeeping consistent, even when the results feel counterintuitive. It also allows interference because phases can reinforce or cancel, and the cancellations are as real as the reinforcements. Interference is the signature that the wave function is more than ignorance about hidden classical facts, because ignorance cannot create phase. Amplitudes can add or cancel, producing patterns no classical probability can mimic, even when particles arrive one by one and never meet. In the double slit experiment, closing one slit changes outcomes at the other, not by force, but by removing paths that contribute phase. What changes is not a push in space, but the set of allowed histories that the quantum system can explore. The microscopic world is probabilistic, yet it is precise in the way probabilities are assigned, and precision is exactly what makes the mystery durable. Pause on the visual. 2 narrow slits cut into a metal plate, lit by a coherent source that keeps phase relationships intact. Behind them, a detection screen glows faintly, and an interference fringe pattern appears like a fingerprint, bright bands alternating with dark. The pattern is not drawn by a wave of matter splashing through space, as if electrons were tiny droplets. It is drawn by the rulebook that adds complex amplitudes, then squares them into probabilities, and it does so whether we watch or not. Quantization is the next key idea, and it appears whenever a system is constrained by boundary conditions, symmetry, or confinement. Electrons in atoms occupy discrete energy levels, not a continuum, because their wave functions must fit the Coulomb potential, with allowed standing wave patterns. In the older Bohr model, the discreteness was imposed, but in wave mechanics it emerges from solving an eigenvalue problem with normalizable solutions. Photons carry energy in packets proportional to frequency, with E equals h nu, a relation that emerged from Planck's attempt to explain blackbody radiation and was sharpened by Einstein's light quanta. Vibrations in a bound system come in allowed modes, like notes that cannot slide continuously, because only certain wavelengths are compatible with the system's geometry. These discrete levels are not optional details or mathematical decoration, and they show up wherever we look closely enough. They explain why atoms are stable, because electrons cannot radiate energy continuously and spiral into the nucleus, as classical electrodynamics would predict. They explain why chemistry has structure, because valence and bonding depend on quantized orbitals and the Pauli exclusion principle, which forbids identical fermions from sharing a state. They explain spectral lines that act like barcodes for elements, letting astronomers read the composition of stars from light alone, across unimaginable distances. They also hint that nature may prefer countable states over continuous ones, at least in certain contexts, and that hint will matter later. Historically, this was not a gentle transition from classical ideas, and the human story mirrors the conceptual rupture. The old picture of tiny planets orbiting a tiny sun failed, and the new picture replaced trajectories with probability clouds and operators. Debates over what the wave function really is were not academic theatre, because the theory kept winning without settling the interpretation. In the early 20th century, physics absorbed a lesson that still echoes here. When equations demand discreteness, the universe often agrees, even if our intuition protests. Quantum fields extend the idea beyond particles as tiny objects moving through empty space, and they do so with a kind of inevitability. In modern language, particles are excitations of fields that fill space, and those fields are the primary entities, defined at every point. An electron is a localized ripple in the electron field, and a photon is a ripple in the electromagnetic field, carrying energy and momentum in quantized units. The vacuum is not empty in the classical sense because it is the lowest energy state of fields, still capable of fluctuations and virtual processes. Those processes momentarily borrow energy within the limits of uncertainty, and they leave measurable traces in the real world. Picture the vacuum as a dark ocean that never fully stills, even when the surface seems calm. Even when no real particles are present, the surface quivers with subtle statistical motion, too small to see directly, yet powerful enough to shift atomic energy levels. The Lamb shift and the Casimir effect are reminders that nothing in quantum theory has structure, and that emptiness has a measurable stiffness. Those fluctuations are usually small and controllable, at least when the interactions are weak and the coupling is gentle. In quantum electrodynamics, calculations match experiments to many decimal places, including the electron's magnetic moment with astonishing agreement, a triumph of both theory and measurement. The theory works because interactions can be treated as perturbations around a simple starting point, and because renormalization organizes infinities into measurable parameters. In practice, we redefine masses and charges in a disciplined way, and the predictions remain stable when we change the arbitrary cutoff. The success is so complete that it becomes a standard for what a fundamental theory should deliver: predictive power without endless ad hoc repairs. Yet even here, a quiet warning is present. Like a hairline crack in a perfect lens, the mathematics often passes through infinities and then subtracts them in a disciplined way, and the discipline is what saves the predictions. Renormalization is not cheating, but it is a sign that short-distance behavior matters, and that the ultraviolet can threaten our descriptions. It invites a question that we usually postpone. What is the theory really saying at arbitrarily small distances, where our approximations become aggressive? Now we turn to the other rulebook, which begins from a different premise. General relativity does not treat gravity as a force acting in space, like an invisible pull across distance, even though that picture is useful in daily life. It treats gravity as the curvature of spacetime itself, a dynamic geometry that responds to energy and momentum, including pressure and stress. Objects follow geodesics, which are the straightest possible paths in a curved geometry, even when those paths look like arcs to our intuition and to our diagrams. The core statement is compact and severe, and it is written in Einstein's field equations, a set of coupled nonlinear relationships. Mass and energy tell spacetime how to bend, and the phrase is not a slogan, but a literal mapping from the stress-energy tensor to curvature. Curved spacetime tells matter and light how to move, so motion becomes a response to geometry rather than a response to a force. The equations relate the distribution of energy and momentum to the geometry of distances and times, and they do so locally, point by point, as if the universe is solving a geometric balance sheet everywhere at once. For visuals, imagine a grid drawn across a dark plane, then pressed down by a heavy sphere, the lines tightening and warping. The grid curves, and marbles roll along the deformed lines, not because they are pulled sideways, but because straight has changed. The analogy is imperfect, because it hides the role of time and it uses an external gravity, yet it captures the central shift. Gravity is geometry, and geometry is physical, with measurable consequences for clocks and rulers. This is not an abstract metaphor or a poetic rebranding of Newton's law, and the historical record is unusually sharp. It predicts the precession of planetary orbits, including the extra rotation of Mercury's perihelion that puzzled 19th century astronomers and resisted conventional fixes. It predicts the bending of starlight, confirmed during the 1919 solar eclipse, when stars appeared slightly displaced near the Sun, and the result became a public turning point. It predicts gravitational time dilation, measured by clocks on satellites and on Earth, and corrected for every time your phone uses GPS, quietly keeping modern navigation honest. It predicts gravitational waves, ripples in geometry detected from merging black holes, arriving at Earth as minute stretches and squeezes smaller than a proton, extracted from noise by patient statistics. Relativity also changes what we mean by causality, and it does so with geometric clarity rather than philosophical debate. The speed of light sets the structure of light cones, which divide space-time into regions of possible influence and regions forever out of reach. Light cones define which events can influence which other events, and they define what before and after can mean when observers move differently. This causal structure is built into the geometry, not added as an afterthought, and it becomes crucial when horizons appear and information becomes one way. In everyday conditions, space-time curvature is gentle, and the world looks comfortably classical, almost forgiving. We can treat space and time as nearly flat and use Newton's approximation, which is essentially the slow-motion weak field limit of Einstein's equations. That approximation works because gravity is weak and velocities are small compared to light, so relativistic corrections hide beneath measurement noise. The smooth, manifold picture of space-time feels natural because it matches our scale, our senses and our engineering. Bridges stand, planets orbit, and clocks mostly agree. The tension begins when we ask for a single framework that includes both rulebooks without contradiction, because each one assumes something the other refuses. Quantum mechanics assumes a fixed background time to define evolution, so states change with respect to an external clock that is not part of the system. General relativity makes time part of the dynamical system, shaped by energy and motion, and even sliced differently by different observers. One theory wants a stage with a consistent metronome. The other says the stage is a player, and players cannot also be fixed reference frames. At modest energies, we can ignore the conflict and patch the theories together, and physics proceeds with impressive success, which can be misleading. We quantize fields on a curved background and get useful results, as long as the background curvature is treated as classical and slowly varying. We compute particle creation near horizons and in expanding universes, where the definition of vacuum depends on the observer and on the chosen notion of time. These hybrid methods work as approximations, but they are not a final union, because the geometry itself remains unquantized, and the bookkeeping breaks when curvature becomes violent. The collision becomes unavoidable when gravity is strong and distances are tiny, because then the background cannot be held fixed without circular reasoning. Black holes are the clearest stress test, because they compress mass energy into regions where curvature becomes extreme and tidal forces become lethal. General relativity predicts that collapse can produce a singularity, a region where curvature becomes infinite and geodesics end, as if space-time itself frays. The equations keep going in a formal sense, but the meaning of the solution breaks, as if the map continues while the terrain disappears. A singularity is not just a dramatic location on a diagram, and it is not merely a point we choose to ignore for aesthetic reasons. It is a sign that the classical description has been pushed past its domain, like using fluid equations inside an atom where molecules matter. Infinities in curvature imply that the smooth geometry assumption fails, because no physical measurement can accommodate infinite tidal forces or infinite energy density. The theory is telling us in its own language that it cannot be the whole story, and that the missing pieces are not optional. The Big Bang is the second collision point, and it is more personal because it is our origin story and our boundary condition. If we run the cosmic expansion backward using classical relativity, density and temperature blow up, and space-time seems to pinch into a boundary. Time appears to begin at a singular edge, where the equations no longer specify what comes next, and where before may not even be defined. Again, the mathematics signals a breakdown of the classical picture, and the signal is too consistent to dismiss as a mere artifact. Quantum mechanics cannot simply be added at the end, like a patch sewn onto a torn fabric after the damage is done. Near such extremes, quantum fluctuations of matter become huge, because high energies activate short-distance degrees of freedom and amplify vacuum jitter. Those fluctuations gravitate because energy is a source of curvature, and pressure contributes as well, which is easy to forget in Newtonian language. The geometry itself should fluctuate because it is coupled to quantum sources, and because the metric is not a passive background in Einstein's theory. The stage should become uncertain, and uncertainty about the stage is a different kind of uncertainty, one that threatens the meaning of distance. This is where the Planck scale enters as a suspected boundary, not as a location but as a regime where our usual separation of ideas fails. It is defined by combining constants from quantum mechanics, relativity, and gravity. Planck's constant, the speed of light, and Newton's gravitational constant. When these constants are mixed, they produce natural units that set a scale for quantum gravity, a scale where neither rulebook can be safely ignored. The remarkable fact is not the numbers themselves, but the dimensional analysis already hints at a new domain. The Planck length is about 1.6 times 10 to the minus 35 meters, a number so small it defeats ordinary comparison and even strains language. If an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand in that scaled-up picture. The Planck time is about 5.4 times 10 to the minus 44 seconds. The time light takes to cross a Planck length, a tick so short that before and after become slippery. These numbers are not just small, they are far beyond the reach of current experiments, and they are small enough that the very notion of distance may change. The Planck energy is enormous by particle physics standards, around 10 to the 19 giga-electron volts, and it is tied to gravity's weakness at accessible scales. That is many orders of magnitude beyond the energies reached at the Large Hadron Collider, which already represents a triumph of engineering and international coordination. To probe a distance, we typically need a particle with a wavelength that small, which means a momentum that large. Concentrating that much energy into that smaller region triggers gravity in a new way, because energy density curves spacetime, regardless of what form the energy takes. This is the key operational problem, and it is not a matter of ambition alone or a temporary lack of funding. To see smaller structure, we build higher energy colliders, because shorter wavelengths resolve finer detail, like sharper light in a microscope. Higher energy means more energy packed into less space during a collision, even if only for an instant and even if it disperses quickly. But gravity responds to energy density, not to our intentions, and it does so universally without a switch to turn off. At some point, the probe becomes the obstacle, because the act of probing changes the geometry you're trying to probe. A thought experiment makes the point without requiring new machines, and it reveals the logic with unusual clarity and very little hand-waving. Imagine trying to localize an event within a Planck length, so you squeeze the wave function into a tiny region and demand a sharp position. Quantum mechanics demands high momentum uncertainty, which implies high energy concentrated in that region, because energy and momentum are linked. General relativity says that enough energy in a small region can form a black hole, creating an event horizon that blocks information from escaping. The attempt to measure creates a horizon that hides what we tried to resolve, turning resolution into concealment and turning curiosity into a kind of self-inflicted blindness. Picture the sequence as a visual zoom, smooth at first and then increasingly granular. We dive past galaxies, past stars, past atoms, past quarks, until the image becomes a vibrating haze of probabilities and fleeting tracks. Then, at the moment we push harder, a dark circle blooms, an emergent horizon, like a lens cap snapping shut over the smallest scales. The universe does not merely refuse to answer, it changes the conditions so the question cannot be completed. This is not a technological limit like a weak magnet or a noisy detector, and it is not simply a statement about today's budgets. It is a candidate for a fundamental limit implied by combining the two rulebooks into one operational procedure, where each step is reasonable by itself. It suggests that spacetime may resist arbitrary subdivision, not by decree, but by dynamics, as if geometry has a built-in back reaction. It suggests that the question of what happens below a certain scale may be physically ill-posed, because the act of asking requires conditions that erase the answer. Still, we must separate two kinds of limits, because confusing them leads to bad metaphysics and premature conclusions. One kind is practical and contingent, based on engineering, money, and time, and history is full of practical limits later overcome by new methods. The other kind is principled, based on what any measurement procedure would require, even with perfect technology and unlimited patience. The Planck barrier is interesting because it may be of the second kind, and because it emerges from the very structure of our best theories, not from a lack of imagination. If that barrier is real, then quantum gravity is not just another force to quantize with familiar methods, like an extra term in a Lagrangian. It is the missing bridge that decides what spacetime is at the deepest level, and what distance even means when geometry is uncertain. A successful theory must reproduce general relativity when curvature is gentle, and scales are large, because we have tested that regime with exquisite care, from solar systems to binary pulsars. It must reproduce quantum mechanics when gravity is negligible, and systems are microscopic, because every modern device depends on that accuracy, from lasers to transistors. It must also do something harder, and this is where many proposals falter under their own weight. It must make sense of situations where both are essential, like black hole interiors and the earliest moments of the universe, without breaking probability or causality. It must remove or reinterpret singularities, because infinities are usually signs of a wrong description rather than physical facts, and physics has learned that lesson repeatedly. It must explain why spacetime looks smooth at large scales, even if it is not smooth underneath, and why classical geometry emerges so reliably. Attempts to quantize gravity as a standard quantum field theory run into a familiar wall, and the wall has a technical name: non-renormalizability. Point-like interactions probe arbitrarily short distances, and virtual processes at high energies contribute divergences that grow worse at each order. In a renormalizable theory, those divergences can be absorbed into a finite set of parameters, preserving predictability and letting experiments fix the unknowns. For gravity treated as a point-particle field theory, the required fixes multiply without end, and the theory loses predictive power because it needs infinitely many inputs, which is another way of saying it stops being a theory. This is where the promise of strings begins to sound less like poetry and more like engineering, because it targets the ultraviolet problem directly. If the fundamental objects are extended, interactions are smeared over a small but finite length, rather than forced to occur at a mathematical point. The ultraviolet behavior softens because there is no single point where everything must happen, and scattering amplitudes can become better behaved at high energies. The mathematics can avoid certain infinities that plague point particles, not by cancellation alone, but by changing what short distance means, and by limiting how sharply interactions can localize. The idea is simple enough to state in one breath, yet deep enough to reshape the story and the imagery we use. A string has modes of vibration, and those modes are quantized like the harmonics of a musical instrument, with frequencies set by tension and boundary conditions. Different vibrational patterns correspond to different masses, charges, and spins, as if the particle zoo is a spectrum of notes played on one underlying object. Quantizing those modes produces a spectrum of particles, and the structure is constrained by consistency conditions that are surprisingly strict, leaving less freedom than our imaginations would like. Among the modes of a closed string is a massless spin to excitation, a particular pattern that cannot be removed without breaking the theory's internal consistency. A massless spin 2 particle behaves like a graviton, the quantum carrier of gravity, because spin 2 fields couple universally to energy and momentum, not to a special kind of charge. This is not merely a resemblance in name or a convenient analogy for outreach materials. In the low energy limit, the interactions implied by that mode reproduce Einstein's equations, as if general relativity is the long-distance shadow of the string's quantum consistency, projected onto familiar scales. Gravity then is not bolted on as an optional feature or an afterthought, and that is part of the historical appeal. It emerges as a required feature of the theory's internal logic, which is part of why the idea attracted attention in the first place, especially after the renormalization struggle. The same structure that organizes particle states also produces a geometric interaction at long distances, and it does so in a way that hints at unification. In that sense, string theory answers the demand that quantum gravity must recover relativity on large scales, while still speaking the language of quantum states and amplitudes. The theory also suggests a new intuition about short-distance physics, and it is counter to our usual expectations about microscopes and resolution. When you try to probe a string at higher energy, you do not necessarily see smaller structure, as you would with a point particle and a shorter wavelength. You can excite higher modes and make the string spread, increasing its effective size in the process, so the object resists being pinned down. The probe becomes fuzzier as you push harder, which hints at a built-in minimum effective length, not as a postulate but as a dynamical response. This is one route to the darker possibility raised in the opening hook, and it lands with a quiet kind of gravity, reality might have an edge, not as a wall in space, but as a limit on resolution, an end to the infinite zoom that our mathematics likes to assume. The edge would be defined by consistency between quantum uncertainty and gravitational collapse, and by the extended nature of the fundamental objects. The universe could be continuous in appearance, yet finite in the information it can contain, because information requires distinguishable states, and distinguishability may have a ceiling. Cosmology keeps the pressure on this idea, because the early universe likely passed through Planckian conditions, where our approximations become fragile. At very early times, densities and temperatures approach the regime where quantum gravity matters and classical geometry becomes suspect, possibly even meaningless. Any claim that the universe is finite or bounded must confront what happens near that beginning, because the beginning is where the rulebooks must become one. Initial conditions are not just a detail, they are the place where a unified theory must speak clearly or admit that it cannot, and that admission would be a result too. Inflation, if it occurred, amplifies tiny fluctuations into cosmic structure, turning microscopic randomness into macroscopic pattern with visible consequences. Those fluctuations begin as quantum variations in fields, stretched by rapid expansion, until they become seeds for galaxies and the large-scale web. Their imprint is seen in the cosmic microwave background, a faint afterglow mapped with increasing precision, and in the distribution of galaxies across billions of light-years. If quantum gravity modifies physics at the earliest times, it could alter what fluctuations are allowed, how they begin, and what statistical fingerprints they leave behind, even if the changes are subtle. Visually, the cosmic microwave background appears as a mottled sphere, a baby picture of the universe with temperature variations at the level of parts in 100,000. The colours are false, but the pattern is real, and it wraps around us like a shell of ancient light. Those tiny blotches are not noise, they are fossilised quantum fluctuations, preserved in radiation that has travelled for nearly the age of the cosmos, carrying a message from a time when the universe was opaque. Black holes offer the other cosmological connection, because they link gravity, thermodynamics, and information in a way that feels like a coded message left in the equations. Horizons behave like one-way membranes, hiding interior details from outside observers and dividing spacetime into regions with different causal access. Black hole entropy scales with horizon area, not volume, a result sharpened by Bekenstein and Hawking in the 1970s and anchored in the physics of temperature and radiation. That area law hints that information content is bounded by surfaces, as if the degrees of freedom of a region live on its boundary, and as if volume is not the true counting measure. This area scaling feels like a clue that spacetime degrees of freedom are not what they seem, and the clue points toward finiteness with unsettling calm. If a region's maximum entropy is proportional to its surface area, then the number of distinguishable states inside may be limited, no matter how smooth the interior looks to classical eyes. What does it mean for a three-dimensional volume to have its information counted on a two-dimensional boundary, as if nature keeps its records on the edge? Is space-time, at the deepest level, more like a ledger than a continuum? And if so, who is allowed to read it? A finite information bound is another sense in which reality could be finite, even if space extends without end and without a center. Space could stretch indefinitely, yet the number of distinguishable states in a region could be limited by gravity and quantum mechanics together, like a maximum storage density. The universe could be a vast stage with a restricted script, where not every imagined configuration is physically realizable, even in principle. Quantum gravity would then be the theory that explains why the script has a maximum density of lines, and why that density is tied to geometry, not to materials. At this point, the chapter's tension is clear and deliberate, and it has been earned by a century of evidence and a mountain of data. Quantum mechanics is probabilistic but exact in its predictions, and it treats measurement as a special kind of interaction with statistical outcomes and irreversible records. General relativity is geometric and deterministic in its classical form, and it treats spacetime as a smooth field that responds to energy, including energy we cannot see directly. Both are confirmed with precision, yet they disagree about the nature of the stage and the meaning of measurement, especially when the stage itself should fluctuate. The Planck scale stands as the suspected border where the disagreement becomes physical, and where words like point and instant may lose their authority. It is where attempts to measure smaller distances may create horizons, turning experiments into gravitational traps that hide their own targets. It is where the smooth manifold may dissolve into something else, perhaps a quantum geometry with new degrees of freedom and new constraints. It is where the question of finiteness becomes more than philosophy, because it becomes operational, tied to what any observer can in principle extract. We do not claim yet that spacetime is discrete, or that strings are the final answer, or that the universe has a literal smallest pixel waiting to be discovered. We only tighten the problem until it cannot be ignored, because singularities are warnings and boundaries are clues, not trophies. Singularities in black holes and the Big Bang are signs that classical geometry is incomplete, not medals for mathematical bravado, or invitations to accept infinities as real. The Planck units give a concrete scale where new rules may appear, and where old intuitions may fail, even if our instruments never reach it directly. String theory enters as a candidate bridge with a specific promise, and the promise is technical before it is philosophical or aesthetic. Extended objects smear interactions and can tame ultraviolet infinities, changing the short-distance behavior that ruins point-particle gravity. A graviton mode appears naturally, suggesting gravity is built in rather than appended, and that suggestion is unusually specific. But the cost is high, because consistency demands extra structure beyond familiar spacetime, and the theory's mathematics refuses to stay confined to 4 dimensions, no matter how much we prefer it. That cost will become the next step in our path, and it will reshape what we mean by where and how many directions are available to reality. If strings are consistent quantum objects, they do not live comfortably in 4 dimensions because anomalies and consistency conditions push the theory toward additional dimensions. The mathematics leans toward extra symmetries as well, narrowing what can exist without contradiction, and that narrowing is both a constraint and a guide. The proposed solution space is wide, and it changes what we mean by a universe, because it changes what counts as a possible geometry and what counts as stable. Now we transition from the problem to the proposed solution space. We move from the clash of rulebooks to the core idea that strings replace points, and we follow that replacement into its unavoidable consequences. We ask why that replacement demands extra dimensions and what those hidden directions might mean for finiteness, information, and the limits of resolution. The door opened in 1968 because a formula hinted at extension, a mathematical structure that behaved as if particles had length rather than being featureless points. Here, extension becomes a strategy for surviving the Planck scale without contradiction, and for turning singularities into questions rather than endpoints. In the next chapter, we follow that strategy into the strange requirement that spacetime has more directions than we can see, and we ask what kind of reality could hide them in plain sight, while still shaping everything we observe. The door opened in 1968 with a scattering formula that behaved like harmony, and the surprise was that it looked less like bookkeeping and more like music. Physicists were trying to understand the strong force, yet the mathematics kept hinting at something deeper, an object that refused to be a point. Chapter 2 showed why harmony matters, because point particles make quantum gravity mathematically unstable at extreme scales. Now we step into the proposed mechanism, where the basic object has length and internal motion. In ordinary quantum field theory, a point particle traces a world line through space-time, like a thin thread drawn across a dark stage. When 2 particles interact, their world lines meet at a single mathematical point, and that perfect localization becomes a problem at very high energies. The ultraviolet catastrophe in gravity is not just a technical nuisance, because the integrals that describe quantum fluctuations blow up as we push to shorter distances. The closer we force the interaction to a point, the more violently the theory responds. A string changes the picture in a way that is small in geometry yet huge in consequence. A point particle traces a world line, but a string traces a world sheet, an extended surface swept out as it moves. Instead of a vertex where lines meet, an interaction becomes a smooth patch where a sheet splits or merges. That small change reorganizes the ultraviolet behavior, because the theory no longer demands perfect localization at arbitrarily tiny scales. The promise is not aesthetic but structural, because smoothing interactions can soften the infinities that plague gravity. Visually, imagine a black background with a luminous ribbon moving forward in time. Where a field theory would draw sharp corners and hard junctions, string theory draws rounded seams, like fabric being stitched rather than wires being soldered. The world sheet can be parameterized by 2 coordinates, often called sigma and tau, which track position along the string and its evolution in time. Those coordinates are not spacetime coordinates themselves, yet they map into spacetime through the string's embedding. That mapping is where geometry and quantum mechanics begin to speak the same language. In string theory, the fundamental entity is a one-dimensional object under tension, and tension here is not a metaphor but a physical parameter. The tension sets the energy cost of stretching the string, and it determines the characteristic length scale, usually written as the square root of alpha prime. When the string vibrates, its oscillations are quantized in the same way that a violin string supports discrete harmonics. But unlike a violin, the string vibrates in multiple transverse directions, and those patterns correspond to different quantum states. The spectrum is not a small list, but an infinite tower of modes. Each mode is a different pattern of vibration, and each pattern appears as a different particle when viewed from far away. The mapping is precise enough to be a claim, not a metaphor, because the quantized excitations carry definite mass, spin, and other quantum numbers. Energy in a vibration contributes to mass through relativity, so higher modes typically look heavier when measured in 4 dimensions. The geometry of the vibration encodes spin, because the oscillation pattern transforms under rotations in spacetime. In plain terms, the string's internal motion shows up as the particle's identity. The quantization procedure makes this concrete. One expands the string's coordinates into normal modes, promotes the mode coefficients to operators, and imposes commutation relations that mirror the uncertainty principle. Physical states must satisfy constraints that come from reparameterization invariance on the world sheet, which is the statement that the physics does not depend on how we label points on the string. Those constraints remove unphysical polarizations and keep the spectrum consistent. They also foreshadow why spacetime dimensions cannot be chosen freely. Charges and other quantum numbers can arise from how the string's endpoints or internal degrees of freedom transform under symmetries. In some formulations, additional world sheet fields, fermions or internal currents, carry representations of gauge groups. In others, the geometry of the compact dimensions supplies the structure, because fields can wrap non-trivial cycles and inherit discrete data. Either way, the theory does not merely add particles by hand, because the allowed excitations are dictated by the same quantization rules. The particle list becomes a consequence of the object's possible motions. Open strings have endpoints, and their boundary conditions matter in a very literal way. At each endpoint, the string can satisfy Neumann conditions, allowing motion, or Dirichlet conditions, fixing the endpoint to a subspace. Those boundary choices are not decorative because they determine what kinds of excitations are allowed and how they interact. Endpoints can also carry gauge charges, which appear mathematically as labels called Chan, Peyton factors. With those labels, an open string state transforms like a matrix, and the gauge symmetry emerges from how those matrices multiply. Open strings naturally produce gauge bosons, the carriers of forces like electromagnetism and the nuclear interactions. The massless spin-1 modes behave like photons or gluons in the low energy limit, and their interactions reproduce the structure of Yang, Mill's theory. In a visual sequence, the world sheet of 2 open strings can join into one, or one can split into 2, with the endpoints tracing clean boundaries. The interaction looks like a smooth pair of pants diagram, not a sharp vertex. That smoothing is one reason the high-energy behavior becomes gentler. Closed strings form loops with no endpoints, and their boundary conditions are periodic, like a ring that can vibrate endlessly. Because there are no endpoints to carry separate charges, closed string modes tend to couple universally, responding to energy and momentum rather than to a specific gauge label. Among their massless modes is a spin-2 excitation with universal coupling, and that is the crucial fact. A massless spin-2 particle that couples universally behaves like a graviton, which means gravity is not optional in the theory. The theory does not decide whether to include gravity, because the spectrum forces it. The low-energy limit reproduces general relativity's structure, but it does so in a distinctive way. When one computes strings scattering at energies far below the string scale, the effective action contains the Einstein, Hilbert term plus additional fields and higher curvature corrections. Those corrections are suppressed by powers of the string length, which makes them small at ordinary energies. In that regime, Einstein's geometry becomes an effective description of string dynamics, like a long wavelength approximation to a deeper microscopic motion. Gravity appears as the collective behaviour of the closed string sector. This is where the chapter's mystery deepens, because consistency becomes a kind of architecture rather than an afterthought. The world sheet theory must preserve conformal symmetry to remain well-defined after quantization, meaning it must be invariant under local rescalings of the world sheet metric. Conformal symmetry is what lets us treat the world sheet metric as a gauge choice, removing redundant degrees of freedom. If that symmetry fails at the quantum level, negative norm states and probability violations appear, and the theory stops making physical sense. The demand for unitarity and gauge invariance becomes a demand on spacetime itself. Historically, this was one of the strangest reversals in theoretical physics. In particle physics, we usually choose spacetime first and then place fields inside it, adjusting the theory to fit observations. In string theory, the requirement that the world sheet quantum theory be consistent constrains the dimension of spacetime, the allowed background fields, and even the gauge structure. It is as if the mathematics refuses to run unless the stage has the right number of dimensions and the right symmetries. That refusal is not philosophical, because it shows up as precise anomalies in calculations. When the world sheet is quantized, anomalies can appear as quantum violations of classical symmetries. An anomaly is not a small correction, because it breaks the rules that keep the theory consistent. On the world sheet, the conformal anomaly is measured by the central charge, which counts degrees of freedom in a way that survives quantization. If the total central charge does not cancel, the theory loses conformal invariance, and the constraints that remove unphysical states no longer work. In spacetime language, the theory would contain ghosts, states with negative probability. In string theory, anomaly cancellation is a gatekeeper, allowing only certain combinations of fields and dimensions. The mathematics does not politely adapt to 4 dimensions, even if 4 dimensions match our senses. Instead, the bookkeeping of quantum symmetry forces a critical dimension, where the conformal anomaly cancels and the theory becomes consistent. The result is not a guess, but a derived requirement, obtained by counting contributions from coordinates, world sheet fermions, and ghost systems. The arithmetic is unforgiving, and it is one of the reasons string theory feels both rigid and alien. For the bosonic string, that number is 26, which is historically important but physically incomplete. It is important because it was the first consistent quantized string theory, and it taught physicists how extended objects could tame ultraviolet behavior. Yet it contains a tachyon, a mode with negative mass squared that signals an instability of the assumed vacuum. It also lacks fermions, which makes it unable to describe the matter we observe. The bosonic string is a classroom model, revealing but not the final story. For superstrings, the critical dimension is 10, and that is the version tied to realistic matter. Supersymmetry on the world sheet introduces fermionic degrees of freedom that balance the bosonic ones, changing the central charge and removing the tachyon in stable formulations. 10 is not chosen for drama, but forced by the same quantum consistency conditions that demanded 26 before. The number appears when the conformal anomaly cancels and the spectrum becomes unitary. In other words, 10 dimensions are the admission price for a consistent superstring. The immediate question is practical and unsettling. If the theory needs 10 dimensions, why do we experience only 3 of space and 1 of time? The answer introduces hidden rooms in the geometry, dimensions that exist but are compactified. They are not missing, but small, curled up so tightly that ordinary motion never explores them. The idea is not new in spirit, because Kaluza and Klein in the 1920s already imagined an extra dimension to unify gravity and electromagnetism. String theory revives that intuition, but it multiplies it and embeds it in quantum consistency. A useful analogy is a garden hose seen from far away. At a distance, the hose looks like a one-dimensional line, because its circular cross-section is too small to resolve. Up close, the second dimension is obvious, because you can move around the circumference. Extra dimensions can be like that, present at every point yet invisible at everyday resolution. The analogy also carries a warning. What looks like one dimension depends on the scale of your measurement. Compactification means the extra directions form a compact space with finite size, like circles, tori, or more intricate curved manifolds. A particle moving through spacetime can also carry momentum in those curled directions, but the momentum is quantized because the directions are periodic. That quantized momentum appears in 4 dimensions as additional mass, producing kaluza, clean towers of heavier states. Each rung on the tower corresponds to an integer amount of momentum around the compact dimension. If the compact dimensions are tiny, those states are heavy, which is why we do not see them in low-energy experiments. The size of the compact space sets the energy required to notice it, and this can be stated cleanly. If a dimension is a circle of radius r, then the momentum modes scale like n divided by r, so shrinking r pushes the excitations to higher energies. If the radius is near the Planck length, the corresponding excitations are near the Planck energy. That places direct tests far beyond current accelerators, which is part of the theory's experimental difficulty. The hidden rooms can shape physics while remaining operationally inaccessible. Yet compactification is not only about size, because shape matters as much as scale. The extra dimensions must preserve enough symmetry to produce a stable, consistent 4-dimensional world, and they must avoid generating large anomalies or inconsistencies in the effective theory. They must also allow chiral fermions and realistic gauge groups, which are non-trivial requirements. Chirality is especially delicate because the standard model distinguishes left-handed and right-handed fermions, and many simple compact spaces produce pairs that cancel. The geometry becomes a generator of particle properties, not a passive container. This is where Calabi, manifolds enter as candidate compact spaces, and their appeal is mathematical as well as physical. They are 6-dimensional shapes with Ricci flat metrics and special holonomy, typically SU3, which allows some supersymmetry to survive compactification. In practical terms, that surviving supersymmetry keeps quantum corrections under better control and stabilizes aspects of the low-energy theory. Their topology determines how many families of particles appear and what gauge symmetries survive. Their cycles and holes act like channels that fields can wrap, producing discrete choices that look like particle spectra. To picture a Calabi, the mind needs a translation, because 6 dimensions do not fit into ordinary intuition. Visualizations often show a shimmering folded object, like a coral reef made of geometry, with tunnels and throats that reconnect in unexpected ways. The key is not the picture itself, but what the picture stands for. A space with non-trivial homology, where loops cannot always be shrunk to a point. When strings wrap those non-shrinkable cycles, their energy depends on the cycle's size, and that energy becomes mass in 4 dimensions. Geometry becomes a menu of possible excitations. The link between geometry and physics is one of string theory's central claims, and it changes what law means. Different shapes produce different low-energy effective theories, with different particles and coupling constants. What we call a law of nature can become a geometric consequence of how dimensions are curled. The hidden rooms do not merely exist, they select what can exist in the visible rooms. The same 10-dimensional theory can yield many 4-dimensional worlds, depending on the compact space and the fields threaded through it. Supersymmetry enters as both a symmetry and a stabilizing strategy, and it arrives with a clear motivation. It pairs bosons with fermions, matching force carriers with matter-like partners in a structured way. In quantum calculations, bosonic and fermionic contributions can cancel certain divergences because their loop effects come with opposite signs. That cancellation improves consistency, and it helps remove tachyonic instabilities that appear in simpler string models. Supersymmetry is not merely an ornament, because it is tied to the theory's ability to remain coherent. Supersymmetry also supports the existence of superstrings in 10 dimensions, and it restricts what interactions are allowed. With supersymmetry, anomaly cancellation becomes possible in specific cases, and those cases are rare enough to be memorable. It narrows the set of consistent theories to a small family, including type 1, type IID, type IIB, and the heterotic strings. The narrowing is a clue that the theory is constrained, even when its solution space later becomes enormous. It is a paradox of the framework that it is both selective and prolific. There is also a historical rhythm here, because the field has experienced waves of optimism and doubt. The first superstring revolution in the mid-1980s was driven by the realization that anomalies could cancel in certain 10-dimensional theories, especially the heterotic string with gauge group SO32 or E8xe8. That cancellation was not a vague hope, because it was a precise mechanism discovered by Green and Schwartz. It suggested that quantum consistency might uniquely point toward a unified theory. For a time, It felt as if the hidden rooms were not optional, but inevitable. At the same time, supersymmetry is a prediction with a complicated status, and the documentary must hold that tension honestly. If supersymmetry exists in nature, it must be broken at energies above what we have already explored, because we do not see superpartners at current collider scales. That breaking would hide superpartners from direct detection while leaving indirect effects in precision measurements or cosmology. The absence of direct detection creates tension, but it does not logically remove the symmetry from the high-energy framework. It leaves us with a question that is scientific and philosophical at once. Is the symmetry real, or merely a useful scaffold? The chapter's central question about finiteness returns through the string scale, and it returns with a physical image. A string has a characteristic length, often taken near the Planck length, and that length acts like a built-in resolution limit. If you try to probe shorter distances by increasing energy, you do not reveal a smaller point, because you excite higher vibrational modes and stretch the object. The probe becomes the structure, and the notion of an infinitely sharp interaction loses operational meaning. The theory hints that the infinite zoom may be physically meaningless, because nature refuses to provide a point-like target. This is not just a slogan, because it shows up in scattering amplitudes. In many string calculations, high-energy scattering is softer than in point particle theories, with exponential suppression replacing the power law growth that drives divergences. The worldsheet integrals effectively smear the interaction over the string length, and the result is a built-in ultraviolet regulator that is not imposed by hand. That does not automatically solve every problem, but it changes the ultraviolet story in a way that is hard to ignore. The extended object behaves like a natural filter against infinite localization. The Planck scale is where quantum gravity becomes unavoidable, and string theory claims to live there naturally. The string length and the Planck length can be related, depending on the coupling and compactification volume, so the relationship is not one fixed number. In many scenarios they are close, making strings relevant only at extreme energies. In others, large extra dimensions or warped geometries can separate the scales, creating speculative windows for phenomenology. Even then, the central idea remains that geometry and quantum mechanics must be negotiated together. As we deepen into the hidden rooms, the visuals can shift from particles to architecture. Imagine a four-dimensional grid, representing the spacetime we know, and then imagine faint translucent shapes attached at every point. Tiny loops and folded spaces that shimmer like internal machinery. The compact dimensions are not elsewhere, because they are co-located with every location we can point to. Every step you take in the visible world is also a step past an unseen microstructure. The universe becomes layered, with a macroscopic stage and a microscopic backstage. Now we pivot from particle properties to cosmology, because compactification is not only a static choice. The early universe was hot and dense, and the geometry could have been dynamic rather than frozen. Extra dimensions might have been larger or less stabilized in the earliest moments, when energy densities were enormous and the vacuum was not settled. As the universe cooled, phase transitions could have driven them to compactify, locking in the effective four-dimensional laws. The hidden rooms may have been remodeled during the universe's first instance. This idea reframes the Big Bang as an episode of geometric settling, and it invites a different kind of imagination. Instead of assuming four dimensions from the start, the theory allows a higher dimensional beginning, followed by a symmetry-breaking descent into the world we observe. Cooling can change which vacuum is stable, and which moduli fields acquire masses. The visible universe becomes the outcome of a dynamical selection process, not a fixed stage. The laws of physics begin to look like the residue of a cooling history. Moduli are fields that describe the size and shape of the compact dimensions, and in a sense they are the dials of the hidden rooms. If moduli are light, they can roll in the early universe and affect expansion, because their energy contributes to the stress energy that drives cosmic dynamics. Their potential energy can mimic dark energy-like behavior, or drive inflation-like phases in some models. Stabilizing moduli is therefore not cosmetic, because unstable geometry would produce time-varying constants we do not observe. A drifting compact space would mean drifting particle masses and drifting couplings. In the language of effective field theory, moduli appear as scalar fields, with potentials generated by quantum effects, fluxes, and non-perturbative phenomena. If the potential is too shallow, the moduli evolve slowly and can dominate the energy budget at late times, conflicting with cosmological observations. If the potential is too steep, stabilization can be violent, producing relics or disrupting nuclear synthesis. The challenge is to create a potential that fixes the modulae while preserving a universe that resembles ours. The hidden rooms must be not only small but stable. Cosmology also raises the question of relic signatures, because a dynamic compactification could leave traces. If extra dimensions change size, they could leave imprints in primordial perturbations or gravitational waves, altering the spectrum in subtle ways. If strings or brains form defects, they could create cosmic strings or other extended relics, stretched across the sky like faint scars. These possibilities are constrained by observations, but they keep the theory connected to data in principle. The universe may carry fossils of its higher dimensional youth. A cosmic string in this context is not the same as the fundamental string of the theory, although the names invite confusion. It is an extended object on cosmological scales that could arise from symmetry breaking or from brane dynamics, and it would produce distinctive gravitational effects. It could lens distant galaxies, create line-like discontinuities in the cosmic microwave background, or generate bursts of gravitational radiation. Many searches have been performed, and the bounds are strong, yet the idea remains a bridge between microphysics and the sky. The hidden rooms might announce themselves through gravity rather than through colliders. The mysterious tone is earned here because the hidden rooms might have shaped the larger structures we see. A compact space determines particle masses and couplings, which determine nuclear physics and stellar evolution. Those in turn determine when galaxies form and how they shine, and how heavy elements are forged in stellar cores. The smallest geometry can echo into the largest history, linking subatomic spectra to the architecture of the night sky. It is a chain of dependence that feels almost unsettling in its reach, yet the same mechanism that makes the theory flexible also makes it hard to pin down, and this is where the narrative tightens. There are many ways to compactify 6 dimensions into a Calabi, Yao-like space, and many of those ways preserve the basic consistency conditions. There are many choices of fluxes, branes, and topologies that satisfy the equations, and each choice can shift the low-energy constants. Each choice can lead to a different low-energy universe, with different spectra and couplings. The hidden rooms become a source of multiplicity. Fluxes, in particular, add a controlled kind of variety. They are generalized field strengths threaded through cycles of the compact space, like invisible lines of force trapped in a folded labyrinth. Because the cycles are discrete, the fluxes are often quantized, producing a large but countable set of possibilities. Fluxes can help stabilize moduli by generating potentials, but they also multiply the number of consistent vacua. The stabilizing tool becomes a source of abundance. This is the beginning of the landscape, a vast set of possible vacua, and the word landscape is chosen carefully. It suggests a terrain with valleys and ridges, where each valley is a metastable vacuum with its own low-energy physics. The landscape is not a single model, but a count of consistent solutions, and the count can be enormous. It suggests that string theory may not predict one unique set of low-energy laws. It raises a darker question about scientific explanation, because explanation without selection can become cataloguing. The tension is sharp because the theory is constrained and unconstrained at the same time, and both facts are true. Consistency forces extra dimensions and specific symmetries, which feels predictive and almost inevitable. Compactification offers enormous freedom, which feels evasive and hard to falsify. The chapter holds both truths because both are part of the current state of the idea. The same mathematics that closes doors also opens a corridor of many rooms. Some researchers respond by looking for selection principles, and their questions are as important as their answers. They ask whether cosmological evolution favors certain vacua through dynamics, tunneling or inflationary measures, rather than choosing randomly. They ask whether stability, entropy, or anthropic constraints narrow the options, even if the narrowing is statistical rather than absolute. Each proposal carries its own uncertainties, and each shifts the meaning of prediction. If a theory predicts a distribution, what does it mean to test it? The anthropic angle, when it appears, is often misunderstood as surrender, yet it is better described as a boundary condition on explanation. If the landscape contains many vacua, some will not allow complex chemistry, long-lived stars, or stable structures, and those vacua would not host observers. The question becomes whether such reasoning can be made quantitative, or whether it remains a story we tell ourselves after the fact. The documentary does not need to decide, but it must name the discomfort. Why does the universe have these constants, and not others? This is where the documentary's central question takes on a new edge, because the hidden rooms now imply a hidden menu. If reality has a fundamental limit, it might be expressed as a finite set of consistent geometries, each with its own effective laws. If the landscape is real, the universe could be one region in a larger space of possibilities. The deeper structure of spacetime might be less like a single corridor and more like a building with countless locked doors. The unsettling thought is that physics might describe the building, while cosmology explains which door we occupy. Now we return to the basic objects, because strings are not the only extended ingredients implied by the theory. Open strings suggest surfaces where endpoints can live, which leads to D-branes, and the concept arrives almost as a necessity. If an endpoint is fixed by a Dirichlet condition, it is fixed to a hypersurface, and that hypersurface behaves like a dynamical object. Branes add new ways to compactify and new ways to localize gauge fields. Because open strings ending on a brane generate gauge theories living on its world volume. They also hint that spacetime itself might be assembled from more primitive ingredients. Visually, the scene can shift to a dark void where a sheet floats like a membrane, and tiny open strings flicker as they attach and detach. The brane is not merely a boundary, because it can carry energy, fluctuate, and interact gravitationally. In some setups, our visible universe is imagined as brane-like, with standard model fields confined while gravity leaks into the bulk. That idea is speculative, but it grows naturally from the same boundary conditions we already introduced. The hidden rooms might be not only curled dimensions, but also extended surfaces within them. Even without fully developing branes yet, the direction is clear, and it points toward unification by equivalence. The 5 superstring theories appear different, with different spectra and symmetries, but dualities suggest they are related descriptions of the same underlying physics. Strong coupling in one theory can map to weak coupling in another, changing what counts as fundamental. A particle in one description can behave like a soliton or a brane in another, and the distinction between elementary and composite begins to blur. The hidden rooms might not be fixed rooms at all, but interchangeable descriptions. Duality is a technical statement with a philosophical aftertaste. It says that 2 theories with different variables can produce identical physical predictions, meaning the difference lies in language rather than in reality. In string theory, T-duality relates compactifications on circles of radius r and alpha prime divided by r, exchanging momentum modes with winding modes. That exchange makes the idea of small and large less absolute, because a very small circle can be physically equivalent to a very large one. The geometry itself becomes a kind of symmetry. S-duality adds another layer, relating strong and weak coupling. A theory that is intractable at strong coupling might be solvable by translating it into a dual theory at weak coupling. This is not a computational trick alone, because it suggests that what we call fundamental depends on the regime we are in. The same physics can be described by strings in one limit and by branes in another. The hidden rooms are not just hidden by size, but by perspective. That brings us to the next transition, where unification becomes deeper and stranger. If the string theories are connected, there may be a broader framework that contains them as limits, like different shadows cast by one object. That framework is called M-theory, and it introduces an additional dimension in certain regimes. The story moves from 10 dimensions as a requirement to 11 dimensions as a unifying possibility. The extra dimension is not added casually, because it emerges when strong coupling reveals new degrees of freedom. In this transition, the visuals can become more abstract, as if the camera pulls back from a single corridor into a blueprint. The 5 theories sit like islands, and thin bridges of duality connect them across a dark sea. As the coupling changes, the bridges brighten, and the islands begin to look like coastlines of one continent. The message is that the underlying structure may be larger than any single perturbative formulation. The hidden rooms may belong to a building whose full map is only visible from far above. We end this chapter with a controlled unease, because the mechanism is elegant yet demanding. Strings replace points and soften the Planck scale conflict, but they demand extra dimensions that hide from direct view. Compactification makes those dimensions small, but it also makes geometry responsible for the particles we observe, turning shape into destiny. The landscape multiplies possible low-energy worlds, and the theory's predictive power becomes a question rather than a guarantee. The same framework that promises unity also confronts us with multiplicity. Next, we follow the unifying hints that connect the different string theories, and we follow them into a more spacious idea. We move from vibrating strings in hidden rooms to the larger structure that ties them together, where strings are no longer the only actors. We step toward M theory and the multiverse question, where consistency may imply not one universe, but many. The door that opened in 1968 does not lead to a single hallway. It may lead to an entire hidden city of geometry. Chapter 3 left us with hidden rooms and too many ways to furnish them, and the central question stays sharp. If strings unify physics, what do they imply about spacetime's deepest structure, and about the limits that spacetime might quietly enforce? Visually, imagine a dark museum corridor where each doorway opens onto a different architectural style. The floor plan looks inconsistent at first, yet the walls share the same foundations, and the same faint vibration seems to hum through every room. That hum is the promise of unification, and it is also the warning that our usual geometric intuition may not survive. In the 1980s, superstrings looked like a narrow path, almost austere in its constraints. Consistency forced 10 dimensions and supersymmetry, and anomalies cancelled only in special cases where the mathematics lined up exactly. That rigidity felt like a clue, because nature often hides her choices behind requirements that appear purely logical. The historical pressure here mattered, because quantum field theory had already taught physicists to fear anomalies. An anomaly is not merely a technical nuisance, it is a sign that a symmetry you relied on cannot survive quantization. In a theory that includes gravity, that kind of failure is catastrophic, because it can destroy conservation laws and make probabilities stop adding up. So when superstring theory offered anomaly cancellation as a built-in feature, it looked like a rare gift. The cancellation worked only for particular gauge groups and only with supersymmetry present, as if the theory were insisting on a specific blueprint. For a moment it felt plausible that the universe had left a single trail through an otherwise impossible landscape. Then the framework fractured into a zoo of final theories, and the confidence began to wobble. Physicists had 5 consistent superstring theories, each claiming to be complete in its own language, and each arriving with its own cast of particles and interactions. Type 1 had open and closed strings with gauge group SO32, and its open strings made gauge forces feel almost engineered. Type 2A had non-chiral closed strings and even-dimensional branes, and its spectrum looked balanced between left and right movers. Type IB had chiral closed strings and odd-dimensional branes, and chirality made it feel closer to the asymmetries we see in particle physics. Heterotic SO32 combined left-moving bosons with right-moving superstrings, a hybrid construction that seemed almost like a clever splice. Heterotic E8XE8 did the same with a different gauge structure, and that structure would later become famous for its potential to host grand unified patterns. Each theory lived in 10 dimensions and used supersymmetry to stay stable, because without supersymmetry, tachyonic instabilities can appear like cracks in a crystal. Each had its own spectrum and interactions, and each could produce gravity through closed strings, because a massless spin-2 mode emerges naturally. Yet a unified theory is supposed to be one story, not 5 competing endings, and the discomfort was more than philosophical. Different theories seem to predict different non-perturbative objects, and different strong coupling behaviour, and those differences were not cosmetic. If the final theory depends on which equations you start with, the word final starts to lose meaning, and physics begins to sound like translation without an original language. This was not only an aesthetic crisis, it was a practical one for calculation and interpretation. Perturbation theory gives you a controlled expansion when the coupling is small, but it can hide entire sectors of the theory when the coupling grows. The worry was that each string theory might be describing a different world, and that only one of them could possibly be ours. Now we step into the surprising repair. The repair was not a new particle or a new symmetry, and it did not arrive as a single dramatic equation carved into stone. It was the discovery that the 5 theories were connected by dualities that acted like secret equivalences, bridges that appear only when you stop insisting on one preferred viewpoint. A duality says 2 descriptions can give the same physics, even when they look unrelated at first glance. The variables look different, the objects look different, and the regimes look incompatible, as if one map were drawn in ink and the other in starlight. Yet measurable predictions match when parameters are translated correctly, and that matching is the only loyalty physics ultimately demands. In visual terms, picture 5 islands in a foggy sea, each with its own coastline and terrain. For years, explorers thought the islands were separate, because the waters between them looked too violent to cross. Duality is the moment the fog thins, and you notice submerged land bridges that connect them below the surface. T-duality is the first shock because it confuses size itself, and size feels like the most innocent concept we have. Compactify one dimension on a circle of radius r, so that moving in that direction eventually brings you back where you started. A point particle would simply carry momentum around the circle, and the allowed momenta would be quantized because the wave must fit an integer number of wavelengths. Strings, however, can do something a particle cannot. They can wind. A closed string can wrap around the circle 1 time, or 2 times, or any integer number of times, and that winding number becomes a new quantum label. Momentum modes scale like 1 over r, while winding modes scale like r over alpha prime, where alpha prime sets the string length squared. That scaling is the key because it means the energy spectrum contains 2 towers that move in opposite directions as r changes. Make the circle smaller, and momentum modes get heavier, as you would expect. But winding modes get lighter, because the string has less distance to wrap, and the tension stores less energy. T-duality exchanges those 2 towers, and the exchange is not approximate or poetic. A theory on radius r can be equivalent to a theory on radius alpha prime divided by r, with momentum and winding swapped and the physics unchanged. Small and large become 2 coordinate choices for the same spectrum, and geometry stops being absolute at the string scale. To a narrator's eye, the visual is almost mischievous. The camera pulls back from a shrinking circle, expecting the world to become cramped, and instead the spectrum rearranges itself until the shrinking looks like expansion. The circle becomes a mirror, and the mirror insists that tiny is not a physical verdict. T-duality also changes what we mean by localization, which is a quieter but deeper consequence. A point particle distinguishes small circles from large ones by its momentum modes alone, so it treats the radius as a measurable geometric fact. A string has winding, so it senses topology and periodicity in a new way, and it can treat a tiny circle as physically large because winding becomes light. This is where the idea of a minimum length begins to feel less like speculation. If shrinking a dimension past the string scale simply trades one set of states for another, then trying to probe arbitrarily small distances may be like trying to see past a mirror. The theory does not forbid small radii, it relabels them, and the labels carry the same physics. S-duality is the second shock because it confuses strength itself, and strength is how we decide what is calculable. In perturbation theory, we expand in the string coupling GEs, which controls how often strings split and join. Weak coupling makes calculations tractable, and makes strings look fundamental, because interactions are rare and diagrams behave. Strong coupling makes the expansion fail and invites new degrees of freedom, because processes of all orders contribute at comparable size. In ordinary field theories, strong coupling can mean confinement, emergent composites, or entirely new effective descriptions. String theory adds a sharper twist. Sometimes strong coupling is not a swamp, but a doorway. S-duality says strong coupling in one theory can map to weak coupling in another, and the mapping can invert the coupling, GIGs going to 1 over GGs. What looks elementary in one description can look composite in the dual description, and what looks like a complicated bound state can turn into a simple, fundamental excitation. This changes the meaning of fundamental, which is one of the chapter's recurring themes. If a weakly coupled string becomes a strongly coupled mess, the dual picture can replace it with weakly coupled objects of a different kind. The theory becomes a network of perspectives rather than a single privileged set of equations, an atlas rather than a single photograph. Dualities also connect different compactifications, and this matters because compactification is where low-energy physics is shaped. They relate background fields, fluxes, and geometric moduli in ways that preserve the spectrum, even when the underlying geometry looks different. They imply that many apparently distinct solutions are the same solution written in different coordinates, and the landscape begins to have identifications, not only multiplicity. There is a subtle scientific virtue here, because dualities act like internal consistency checks. If 2 computations done in different regimes agree after translation, it is hard to dismiss that agreement as coincidence. Duality is not experimental confirmation, but it is a kind of mathematical triangulation, and it narrows the space of plausible mistakes. Now the narrative widens again. Dualities did not merely link theories pairwise, like isolated bridges between neighbouring islands. They suggested that the 5 theories were limits of one deeper structure, and that the zoo was an artifact of looking from too close. That deeper structure became known as M-theory, a name that carried deliberate ambiguity. It is not a single finished set of equations in the way quantum electrodynamics is, and it is not presented as a tidy Lagrangian written once and for all. It is a framework inferred from consistency, duality, and strong coupling behaviour, and its confidence comes from how many separate clues converge. Historically, this shift was dramatic because it reframed what it means to solve a theory. In earlier decades, physicists often expected a final formulation to be a specific set of field equations. M-theory suggested a different kind of completion, where the full object is known through overlapping limits, and each limit is reliable only in its own domain. The key claim is simple and unsettling. At strong coupling, an extra dimension can appear, not as a metaphor, but as a measurable geometric direction in the effective description. 10 dimensions are not the end of the story. They are what you see when the coupling is small enough that one direction is effectively hidden. Type 2IA is the cleanest doorway into this idea, because its strong coupling behaviour is unusually geometric. As GEs increases, a new length scale grows, and the radius of an emergent circle scales like GAs times the string length. When GEs is small, that circle is tiny, and the world looks 10-dimensional, because excitations around the circle are too heavy to notice. When GRs becomes large, the circle opens and the world looks 11-dimensional, and the theory's bookkeeping suddenly simplifies. The extra dimension is not added by hand, and it is not chosen for aesthetic symmetry. It is demanded by the spectrum of non-perturbative states, which is the spectrum you cannot see if you insist on perturbation theory alone. In type IIA, there are D0 branes that act like point-like objects in 10 dimensions, and they carry a conserved charge. Their masses scale like 1 over GEs, so they become light at strong coupling, which is exactly when perturbation theory breaks. A tower of such states resembles Kaluza, Klein momentum modes on a circle, where momentum is quantized in integer units. The identification is precise enough to be persuasive, because the mass spacing matches what you would expect from momentum in an extra compact direction. The D0 branes behave like momentum quanta in an 11th dimension, and strong coupling reveals geometry. The message is almost philosophical. What looked like interaction strength in one description becomes size of a dimension in another. To visualize this, imagine a camera hovering over a flat grid that seems complete, until the lighting changes and a hidden staircase becomes visible. The staircase was always there in the structure, but it was too steep to climb when the coupling was small. As the coupling grows, the steps flatten, and the 11th direction becomes traversable. In this picture, strings are not the only basic ingredients, and that is another quiet revolution. M-theory contains membranes and higher dimensional branes as fundamental objects, not merely as convenient solutions. The 2-dimensional membrane is called the M2 brane, and the 5-dimensional brane is called the M5 brane, each with its own dynamics and its own role in the web of dualities. When M-theory is compactified on a circle, the M2 brane wrapped around the circle looks like a fundamental string in 10 dimensions, because one of its directions is hidden in the compact loop. When the M2 brane is unwrapped, it looks like a membrane moving in 11 dimensions, extended and flexible in a way a string is not. The same object becomes different things depending on how you slice the geometry, and the slicing is part of the description rather than part of reality. This is the unifying beat. The 5 superstring theories are not 5 separate universes of math, each demanding allegiance. They are 5 perturbative corners of one non-perturbative structure, and each corner is a limit where a particular expansion works well. The zoo becomes a set of coordinate patches, and the embarrassment turns into a kind of cartographic success. The price of that unity is a shift in intuition, because the true theory may not have a single weak coupling description. It may require multiple overlapping charts, like an atlas that covers a curved planet, where no single map can be distortion-free everywhere. The physics is one object, but the language changes with regime, and the regime is not optional. Now we introduce the actors that make this possible in practice. These act as brains which generalize strings by adding dimensions, and they change the visual grammar of the theory. Instead of only filaments vibrating in space, you now have sheets, volumes, and higher dimensional surfaces that can bend, intersect, and carry fields. A p-brane is an object with p spatial dimensions, and the definition is deceptively simple. A string is a one-brane, extended in one direction like a line. A membrane is a two-brane, extended like a surface. A three-brane has three spatial dimensions and can resemble a universe-sized sheet, which is why the idea of living on one becomes so tempting. D-branes enter through open strings, and the entry point is technical but concrete. An open string endpoint can satisfy Dirichlet boundary conditions, which means the endpoint is fixed to a hypersurface rather than free to roam. That hypersurface is dynamical and carries energy, and in quantum theory, anything that carries energy can fluctuate and interact. It is a D-brane, labelled by its dimension, and it is not an optional add-on. The discovery of D-branes in the mid-1990s was pivotal, because it turned previously mysterious non-perturbative states into tangible geometric objects. What had looked like abstract solitons suddenly had a place to live, and that place had a world volume where physics could happen. The theory gained new handles, and the handles made dualities feel less magical and more mechanical. Open strings ending on a stack of D-branes produce gauge fields on the brane world volume, and this is one of the cleanest mechanisms in the framework. The massless spin-1 modes act like gauge bosons, so electromagnetism-like forces can appear as vibrations constrained to the brane. Chan pattern labels become matrix degrees of freedom, and the gauge group emerges as UN for n-coincident branes, because strings can begin and end on different branes in the stack. The geometry of the stack becomes algebra, and the algebra becomes force. Separate the branes slightly, and some open strings stretch between them, gaining mass like a rubber band under tension. In the low-energy theory, that stretching looks like symmetry breaking, a geometric picture that echoes how the Higgs mechanism gives mass by changing the vacuum. This gives a clean separation of forces, and the separation has cosmological consequences. Gauge interactions can be localized on branes because open strings are attached and cannot leave. Gravity comes from closed strings, and closed strings are not confined to a brane because they have no endpoints to pin down. They propagate through the full higher dimensional bulk, and that freedom is why gravity can behave differently. That separation changes the old unification dream. Instead of forcing all fields to live in the same space-time volume, string theory allows different sectors to live in different places, like instruments in different rooms of the same building. Matter can be trapped on a brane, and gravity can explore extra dimensions, which means unification may not mean cohabitation. Now we pivot from formal consistency to cosmology. If branes are real ingredients, they can shape the universe at the largest scales, and the mathematics stops feeling purely microscopic. The same objects that resolve strong coupling puzzles can also act like cosmic scaffolding, and the scale shift is part of the chapter's intrigue. Braneworld cosmology proposes that our observable universe is a three-brane, a three-dimensional surface evolving through time. Three large spatial dimensions are the brane directions, the directions where our particles and forces move freely. Additional dimensions exist in the bulk, possibly compact, possibly warped, possibly large compared to the string scale, and their geometry can influence what we measure. In this scenario, the weakness of gravity can be reinterpreted, and reinterpretation is not the same as explanation, but it is a useful lens. Gravity looks weak because it spreads into extra dimensions, so its field lines dilute into a larger space. Gauge forces look strong because they're confined to the brane and cannot dilute into the bulk, so their influence stays concentrated. The idea can be stated in one operational image, and it is almost cinematic. Two charges on the brane exchange open strings and feel a force that stays in three dimensions, like ripples trapped on a pond surface. Two masses exchange closed strings and feel a force that can leak off the brane, like sound that escapes into the air above. The gravitational field lines have more room. Different models implement this leakage differently, and the details matter because they determine what could be observed. Large extra-dimension models use volume dilution, where the higher dimensional Planck scale can be lower, while four-dimensional gravity stays weak. Warped models use geometry, where the metric suppresses gravity on the brane even if dimensions are not large, because distances and energies are rescaled by curvature. Either way, the brain world idea makes extra dimensions more than a hidden mathematical requirement. It makes them potentially testable through gravity, which is the one force we have not yet unified with quantum mechanics in the laboratory. It also makes the universe feel less like a self-contained arena and more like a surface embedded in something larger, an island with a deep ocean beneath. Brains also bring new cosmological events into the story, and these events are dramatic without being supernatural. If brains move in the bulk, they can collide, and collision is a natural interaction for extended objects. A collision can release energy into brain-localized fields and resemble a hot Big Bang, because it can flood the brain with radiation and particles. In some ekpyrotic and cyclic ideas, repeated collisions drive repeated cosmological epochs, and the universe's history becomes a sequence rather than a single origin. The appeal is not that it is proven, but that it offers a mechanism where the beginning is replaced by an event in a larger space. The Big Bang becomes less singular in principle, because a violent event can occur in higher dimensions without requiring a space-time boundary in 4. These are not established facts, and the chapter keeps that distinction visible. They are mechanisms allowed by the framework, and allowed is not the same as realized. Still, the existence of such mechanisms changes what we mean by cosmological possibility, because it expands the menu of consistent stories. Now the multiverse enters with more force, and it enters not as a science fiction add-on. It enters as a consequence of too many consistent vacua and too many ways to realize cosmology, once you accept that extra dimensions can be shaped and threaded in many ways. The door to many universes is not painted on the wall, it is built into the architecture. The first mechanism is compactification variety, which is the simplest to state and the hardest to count. The 6 hidden dimensions can be shaped in many topologically distinct ways, and those shapes can include handles, holes, and cycles that cannot be shrunk away. Fluxes can thread cycles in quantized units, like magnetic field lines trapped through a loop, and quantization makes the choices discrete rather than continuous. Brains can wrap cycles and add discrete charges, and those charges constrain what fields can exist and how symmetries break. Each choice stabilizes moduli differently and sets different low-energy constants, because the size and shape of the compact dimensions behave like fields in the 4-dimensional effective theory. Particle masses, coupling strengths, and symmetry breaking patterns can change, and the same underlying theory yields many effective 4-dimensional worlds. The second mechanism is vacuum multiplicity, and it is more subtle because it can occur even within a fixed compactification. The effective potential for moduli and fields can have many metastable minima, separated by barriers. Each minimum is a vacuum state with its own cosmological constant and its own spectrum, and metastable means long-lived enough to look permanent on cosmic timescales. Tunneling between minima is possible through quantum processes, and the picture resembles radioactive decay in an abstract space of fields. A region of space can sit in one vacuum for an enormous time, and then a bubble of a new vacuum can nucleate and expand. The transition is local, but its consequences can be global for the region inside the bubble. The third mechanism is brain dynamics, which adds a kind of combinatorial richness. Different regions of the bulk can host different brain configurations, and brain positions can act like fields with multiple stable arrangements. Collisions and separations can create causally disconnected regions with different physics, not because the laws changed midstream, but because the configuration that realizes those laws differs. Now we add the inflationary amplifier, because without amplification many vacua would remain mathematical footnotes. If inflation occurs in a landscape with many vacua, it can populate them, and it can do so repeatedly. Quantum fluctuations can push regions over barriers, and regions that tunnel to a new vacuum can inflate again, growing enormous and isolating themselves from their neighbours. This produces bubble universes, which are best imagined as expanding domains in a larger inflating background. A bubble is a region that transitions to a new vacuum and then expands, and its interior can have different constants and different symmetry breaking. Bubbles can be separated by domain walls and can be causally isolated by expansion, so elsewhere becomes physically unreachable, rather than merely far away. The multiverse here is not one specific picture, and that nuance is important. It is a family of outcomes that share one feature. The framework allows many consistent low-energy realities, and cosmology can in principle realize more than one. The mystery is not that there are many stories, but that the theory seems comfortable allowing them. This is where the chapter's mystery deepens, because possibility forces a question about selection. If many universes are possible, the question of selection becomes unavoidable, and it is not a question you can postpone forever. Why do we observe this vacuum rather than another, and what would it even mean to answer that scientifically? Some selection ideas are dynamical, and they try to keep the old dream alive. Perhaps certain vacua are more stable and dominate volume, because they decay more slowly. Perhaps tunneling rates favour particular regions, so that some vacua are statistically common. Perhaps cosmological evolution funnels toward attractor solutions, making some outcomes robust regardless of initial conditions. Some selection ideas are environmental, and they accept that typical may depend on who is asking. Observers require long-lived stars, complex chemistry, and structure formation, and those requirements constrain constants like the cosmological constant and the strengths of forces. Many vacua may not allow those, and in that view our vacuum is not typical of all possibilities, but typical of the subset that can host measurement and memory. The anthropic argument is not a proof, and it is often misunderstood as a surrender. It is a conditional statement about what can be observed, not a claim that anything goes. It becomes scientific only if it yields statistical predictions or constraints that can be compared with data, and that comparison is difficult because it requires a measure over possibilities. At this point, it is worth asking a thought-provoking question that sits under the entire discussion. If the laws we see are partly a consequence of where we can exist, does that weaken explanation, or does it redefine what explanation means? The unease comes from wanting necessity, while the mathematics keeps offering contingency. Now we slow down and add scientific caution. Mathematical allowance is not empirical evidence, and a framework can be internally consistent yet irrelevant to nature. Dualities are powerful internal checks, but they do not guarantee that nature uses the framework, and they do not tell us which compactification, if any, describes our world. The strongest claim we can make is conditional, and the documentary keeps that conditional explicit. If string theory is the correct ultraviolet completion of gravity, then extra dimensions and brains are natural, almost unavoidable. If extra dimensions and brains are real, they can leave signatures, and signatures are where speculation meets instrumentation. One class of signatures is deviations from Newtonian gravity at short distances, where extra dimensions could change the force law. If extra dimensions are large or warped, the inverse square law can change below a certain scale, because gravitational flux spreads differently. Precision torsion balance experiments test this down to sub-millimeter ranges and keep pushing, looking for tiny departures that would signal new geometry. Another class of signatures is Kaluza, Klein modes and missing energy at colliders, which would be a more direct hint of extra-dimensional motion. If the compactification scale is low enough, heavy excitations could be produced in high-energy collisions. They could appear as resonances, altered cross-sections, or energy carried off into the bulk, leaving an imbalance in the detector. Another class of signatures is cosmological imprints, where early universe dynamics could leave patterns in the sky. Brain inflation models can produce distinctive non-Gaussianity patterns or tensor spectra, and those patterns can be compared against cosmic microwave background data. Cosmic strings or superstrings could produce gravitational lensing features or gravitational wave bursts, and the search for such signals is now part of multi-messenger astronomy. Another class is astrophysical energy loss, which turns stars into laboratories. If gravitons can propagate into extra dimensions, stars and supernovae could cool differently, because energy could leak away in channels we do not see. Observations of supernova 1987A and other systems constrain such leakage, and those constraints already rule out some versions of large extra dimensions. These are not confirmations, and the chapter refuses to pretend otherwise. They are ways the framework could fail or be supported, and that is the honest posture of frontier physics. The mystery depends on honesty, because a story that overpromises becomes a myth rather than a documentary. Now we return to the deeper implication for finiteness, because the chapter's title is not only about an extra dimension. Duality has already hinted that small can equal large, and that suggests space-time resolution may have a built-in cutoff. Brainers and extra dimensions add new ways to hide information and distribute it, as if the universe were protecting itself from infinite detail. In M-theory, the notion of dimension becomes less fixed, and that flexibility is not just a curiosity. A dimension can emerge at strong coupling, and a geometric parameter can become a coupling constant in a dual description. The the boundary between geometry and dynamics becomes negotiable, and that negotiability is a clue about what spacetime really is. That clue echoes the opening hook about an edge, but the edge may not be a wall. It may be a limit on distinguishable states, enforced by quantum gravity and encoded in duality. If the theory refuses to let you define arbitrarily small distances in an invariant way, then the smallest scale is not a place but a principle. If the landscape is real, finiteness returns in a different form, and it is a finiteness of options rather than a finiteness of space. The number of consistent vacua might be enormous but discrete, because fluxes and charges are quantized. The set of possible low-energy laws might be vast but countable, and reality could be not one continuum of options, but a structured catalogue. Yet the multiverse also threatens to make explanation feel thin, and the documentary holds the tension rather than resolving it. If every outcome exists somewhere, prediction can become selection, and selection can feel like a retreat from the old ambition. The question becomes whether physics is discovering inevitabilities or mapping possibilities with conditional rules. Now we build the mystery into a question that cannot be dodged, because it sits at the intersection of mathematics and meaning. If there are many possible universes, do we live in one selected by necessity, selected by chance, or selected by the requirement that observers exist? Each option carries a different emotional weight, and each reshapes the promise of unification. Necessity would mean a deep principle that picks a unique vacuum, perhaps through consistency conditions we have not yet recognized. Chance would mean cosmological history and tunneling accidents, where our vacuum is a frozen outcome of a probabilistic process. Anthropic constraints would mean we can only find ourselves where complexity is allowed, and the laws we measure are partly a reflection of that filter. Each option changes what unification means, and it changes what we should expect from a final theory. A unique vacuum would make string theory predictive in the old sense, where constants are derived rather than chosen. A multiverse would make it predictive in a statistical sense, if measures can be defined and if typicality can be justified. An anthropic filter would make it predictive only through conditional probabilities, and the condition would be the existence of observers. Now we transition toward the next chapter's theme. The multiverse idea pushes us to ask what counts as a boundary in physics, because boundaries are where finiteness becomes concrete. If spacetime can be a brain in a bulk, then boundaries can be literal surfaces, with fields trapped on one side and gravity roaming beyond. If dualities equate small and large, then boundaries can be informational limits, where description changes because resolution stops being absolute. The next step is to ask whether reality has hard cutoffs, and whether those cutoffs are geometric or statistical. Is spacetime finite in extent or in information capacity? Are there limits set by horizons, entropy bounds, and quantum gravity consistency? Limits that behave like edges even when space itself has no wall. We end with the door still open, because that is the honest shape of the subject. M theory unifies the zoo by turning 5 theories into one structure, and that structure naturally allows brains, emergent dimensions, and many vacua. The multiverse becomes a mathematical possibility, not a bedtime fantasy, and possibility is enough to change the questions we ask, and the darker possibility returns in a new register. If reality is a tapestry of dual descriptions and discrete vacua, then the edge may be built into the rules, not drawn at the end of space. The next chapter asks whether that edge is a boundary of spacetime, a boundary of information, or both, and whether crossing it is even a meaningful idea. The documentary began with a quiet accident in 1968, and with the unease it opened in the background of every later discovery. Strings promised unity by softening infinities, yet they also hinted at an edge, an outer limit where familiar descriptions fail. In this chapter, the edge stops being a metaphor and becomes a set of constraints that physics can name. Some limits are about what we can see, because light and time are finite. Others are about what can exist, even in principle, when gravity and quantum theory share the same stage. We start with the simplest confusion, because it shapes every later claim and every later argument about beyond. The observable universe is not the entire universe, even if it feels like the only one we can talk about honestly. It is the region whose light has had time to reach us since the Big Bang, carried across expanding space. The boundary is a horizon, not a wall, and it moves as the universe expands and as our clocks keep running. When we say horizon, we mean a geometric boundary in space-time, an edge drawn by causality rather than by matter. A horizon is created by two facts that never negotiate no matter how much we wish they would. Light travels at a finite speed, and the universe has a finite age since its hot beginning. Meanwhile, expansion stretches distances while light is in flight, so the path a photon takes is never a simple straight line on a static map. Even if space is infinite, our past light cone is finite, because it is limited by time and by the expansion history. Even if space is finite, the observable region can still be smaller, because the horizon is not the same thing as the universe's total size. In cosmology, the word distance itself becomes slippery, because it depends on how you measure it. There is proper distance, co-moving distance, luminosity distance, and angular diameter distance, each one tailored to a different observation. The expansion history matters, because it decides which events can ever influence us, and which will remain permanently silent. In a decelerating universe, the horizon grows faster, and more of space becomes visible, so the accessible region steadily expands. In an accelerating universe, a future event horizon can appear, limiting what we will ever see even if we wait forever. Distant galaxies can cross that horizon, not by moving through space like rockets, but because space expands between us and redshifts their light into invisibility. This is where the eerie idea first becomes precise, and precision makes it more unsettling rather than less. There can be regions that exist now, with stars and planets and histories, yet can never send us a signal. Unseen is not non-existent, and ignorance is not a proof of absence. It is only causally disconnected given the universe's geometry, its expansion rate, and the finite speed at which information travels. To keep the language honest, we separate two distances that sound similar but are not, because careless phrasing breeds false conclusions. The particle horizon is the maximum distance from which light could have travelled to us since the beginning, given the real expansion history. The event horizon is the maximum distance from which light emitted now will ever reach us, even in infinite future time. One looks backward to what has already arrived, and the other looks forward to what can ever arrive. Visually, these horizons are not circles on a static sheet, but surfaces in space-time that tilt and curve with cosmic time. The past light cone narrows as we look back, because earlier times had less time for light to travel. The future light cone spreads forward, but in an accelerating universe it spreads into a limit, like a flare that never fully opens. The distinction is subtle in words, yet it is sharp in equations and in the geometry of world lines. Inflation complicates the story, because it changes the horizon bookkeeping in a way that feels like a trick until you track the math. A brief period of rapid expansion can push once connected regions far apart, separating them faster than light could ever traverse the growing gap. It can also make the observable universe look unusually uniform, because our patch came from a smaller region that was once thermalized and well mixed. Inflation can hide pre-inflation structure beyond our horizon, even if it still exists, leaving us with a smooth sky and a lingering suspicion. Historically, inflation was proposed to address puzzles that looked like coincidences in the older Big Bang picture. Why is the cosmic microwave background so uniform across regions that seem causally disconnected in a non-inflationary model? Why is the universe so close to spatially flat, as if tuned to a knife edge? Inflation reframes these as natural outcomes of an early exponential-like expansion, which stretches curvature away and enlarges a once small, once connected domain. Yet inflation also sharpens the theme of this chapter, because it makes beyond the horizon more than a casual phrase. If inflation occurred, then our observable universe may be a tiny sample of a vastly larger whole. The smoothness we see could be local, a property of our patch rather than of everything. When we look at the microwave background, we may be reading a chapter of a book whose earlier pages have been torn away by expansion. Now we step from observational limits to spatial finiteness, because the words sound similar and mislead. A universe can be finite in volume, even if it has no edge you could reach by travelling. The key is curvature and topology, not a boundary you could point to in a telescope image. This is a place where intuition fails, because we are trained by rooms, oceans, and continents, all of which have borders. General relativity allows three broad spatial curvatures in simple cosmological models, especially the Friedmann, Lemaitre, Robertson, Walker class. Positive curvature corresponds to a closed geometry, often compared to a three-sphere, where straight lines eventually reconverge. Zero curvature corresponds to a flat geometry, where Euclidean rules hold locally and large triangles behave as we expect. Negative curvature corresponds to an open geometry, often compared to a saddle, where geodesics diverge and triangles have angle sums below 180 degrees. Curvature is local geometry, and topology is global connectivity, and the distinction matters more than it first appears. Curvature tells you how triangles add up, and how parallel lines behave in a neighbourhood small enough to ignore global identifications. Topology tells you whether paths wrap around and return, and whether space has identifications that make distant points secretly the same. A space can be locally flat and still be globally finite, which is a statement that sounds like a contradiction, until you picture it carefully. The three-sphere analogy is the cleanest way to remove the false image of an edge, because it replaces a cliff with a loop. On a two-sphere, you can travel forever, without meeting a boundary, and the surface area is finite. You never fall off the Earth's surface in the geometric model, because off is not a direction that exists within the surface. A three-sphere is the higher dimensional version, where three-dimensional space itself is curved and closed, and there is no external outside required by the mathematics. To make the visuals concrete, imagine a grid painted on a balloon as it inflates, with galaxies sitting at intersections like tiny beads. As the balloon expands, every bead sees others recede, yet no bead sits at a centre on the surface. The analogy is imperfect, because the balloon's surface is embedded in a higher space, while the real universe need not be. Still, it trains the mind to separate finite from bounded, and to accept that closure does not require an edge. But topology can do the same trick without positive curvature, which is where the story becomes even more counterintuitive. A flat universe can be finite if it is a three-torus, where opposite faces are identified in three independent directions. You move in a straight line and eventually return, not because space curves, but because the map wraps and the coordinates repeat. The geometry can be Euclidean locally, while the global volume is finite, like a video game world that loops seamlessly when you cross its border. This is where the title earns its meaning, because the edge of the map might be an identification, not an endpoint. The universe might be finite without a border, and our intuition about outside might not apply at all. Asking what lies beyond could be like asking what lies north of the North Pole, an understandable question that misuses the coordinate system. The edge is not a place you reach, but a rule that defines how space is stitched. We then ask what cosmology can actually test, because topology is not free philosophy and not merely a choice of words. If space wraps, light can take multiple paths to reach us, like echoes in a vast hall. The same region of the early universe could appear in different directions, separated by large angles on the sky. The sky could contain repeating patterns, like a signature of a finite room, whose walls are not walls but identifications. The most famous search strategy is circles in the sky, and it is famous because it is geometrically clean. If the last scattering surface intersects itself due to a wrapped topology, the cosmic microwave background could show matching circles with correlated temperature fluctuations. Those circles would be separated on the sky, yet share the same pattern, as if the same ring had been photographed twice. They would be a geometric echo of a finite topology, stamped onto the oldest light we can see. To appreciate why circles appear, remember what the last scattering surface is in the first place. It is not a physical shell you could touch, but a surface of equal time in our past when the universe cooled enough for electrons and protons to form neutral hydrogen. Before that recombination epoch, photons scattered constantly in a hot plasma, and the universe was opaque. After recombination, photons streamed freely, and those photons are the microwave background we measure today. Another strategy looks for repeating structures in large-scale galaxy surveys, because topology would also duplicate later cosmic structures. If space is compact, some distant clusters or patterns of galaxies might be multiple images of the same object, seen along different wrapped paths. In practice, evolution and noise make this difficult, because galaxies change with time and surveys have selection effects. The CMB remains the cleanest global screen, because it is a single surface with well-understood physics and a nearly uniform origin. Planck satellite data has pushed these tests hard, and the results are cautious rather than triumphant. The CMB strongly favours near flatness in curvature, with spatial curvature consistent with zero within tight bounds. That makes a small, positively curved closed universe less likely, at least in the simplest models. But near flatness does not settle topology. because a large, compact, flat space can mimic infinity over the region we can observe. The constraints often translate into a minimum size for certain topologies, expressed as a lower bound on the fundamental domain. If the fundamental domain is smaller than the observable universe, we would expect obvious repeats, like mirrored patterns or matched circles that stand out statistically. The absence of clear matched circles suggests that if space is compact, it is at least comparable to, and likely larger than, our observable patch. The map might wrap, but the loop might be too large to notice, which leaves the question open in a frustratingly elegant way. That frustration is part of the chapter's mood, because it reveals a pattern we will see again. The universe keeps offering limits that are real, yet it also keeps hiding what lies beyond those limits, behind the same laws that define them. The horizon blocks direct observation, and a large topology hides repetition by making the repeats too distant. The edge is not a single boundary, but a layered set of constraints that conspire to keep the global picture incomplete. Now we tighten the stakes, because cosmic topology is only one kind of finiteness, and it may not be the most fundamental. Even if space is infinite, spacetime might enforce a finite information budget, and the next limits come from quantum gravity. Here, measurement itself becomes dangerous, because the act of probing can trigger gravitational collapse. The edge is no longer far away in the sky, but close to the instruments we imagine building. Quantum mechanics says we can localize a particle by using high momentum probes, because short wavelengths resolve small distances. General relativity says energy curves spacetime, and enough energy in a small region forms a black hole. Put them together, and a paradox appears, not as a poetic tension but as a quantitative conflict. The attempt to see smaller scales can create an event horizon that hides what you tried to see, as if nature responds to curiosity by drawing a curtain. Thought experiments make this concrete without pretending we can build the apparatus, because the logic is already enough. To resolve a length scale dx, you need a probe with wavelength comparable to dx, and that demands high momentum. In simple terms, higher momentum means higher energy, and the energy required grows as the target scale shrinks. If you concentrate that energy into a region smaller than its Schwarzschild radius, the region collapses into a black hole, and the information you hope to extract becomes inaccessible. The Schwarzschild radius is not an abstract symbol here, but a physical threshold defined by gravity's strength. For a mass or energy E, there is a radius at which escape velocity reaches the speed of light, and beyond which causal signals cannot return. The remarkable point is that the quantum requirement for localization and the gravitational requirement for collapse meet at a scale where both become unavoidable. That meeting point is associated with the Planck length, around 10⁻⁵ meters, which is unimaginably small yet conceptually loud. This suggests a minimum operational length, and operational matters because it ties the limit to what can be measured in principle. It is not merely a technological limit, like a microscope we have not yet engineered. It is a limit that follows from combining the two rulebooks we already met: quantum uncertainty and gravitational collapse. Below that scale, the concept of a point in spacetime may stop being physically meaningful, because the act of defining a point summons the very horizon that erases it. String theory fits into this tension in a distinctive way, because it replaces point particles with extended objects. Strings are extended so they resist perfect localization, and their size sets a natural scale for interactions. At high energies, instead of probing smaller distances cleanly, you excite higher vibrational modes and spread the interaction over the string length. Dualities also blur small and large, reinforcing the idea that infinite zoom may be a false expectation, rather than a missing technology. One of the most striking dualities, in plain language, says that physics on a tiny circle can be equivalent to physics on a large circle, with momentum and winding exchanging roles. The universe can hide smallness by translating it into largeness, as if the map folds back on itself at the scale where you expect to find a final pixel. This does not prove that spacetime is discrete, but it undermines the assumption that arbitrarily small distances are always physically distinct. The edge appears again, not as a boundary in space, but as a symmetry that refuses to let smaller mean what we think it means. But the deeper finiteness we confront now is not only geometric, and not only about the reach of our instruments, it is informational, and black holes forced physics to ask how many distinct states can fit inside a region. The answer was unexpected, because it contradicted the intuition built into ordinary quantum field theory. The edge becomes a limit on the number of possible descriptions, not merely on the size of the arena. The key clue came from black hole thermodynamics, a story with a history that reads like a slow reveal. In the early 1970s, Jacob Bekenstein argued that black holes should have entropy, because otherwise the second law of thermodynamics could be violated. If you drop a box of hot gas rich with entropy into a black hole, the entropy seems to disappear from the outside world. Bekenstein proposed that the black hole's horizon must carry an entropy that compensates, preserving the logic of thermodynamics. Stephen Hawking's calculation then gave a precise result, and it changed the subject from speculation to mathematics. Using quantum field theory and curved spacetime, Hawking found that black holes radiate like black bodies, with a temperature set by their surface gravity. The radiation is faint for large black holes and intense for small ones, but its existence is a universal statement. Once black holes have a temperature, they must have an entropy, and the entropy can be computed. The entropy is proportional to the horizon area, not the volume, and that is the shock that changes the map. A naive quantum field theory would expect volume scaling, because it assigns independent modes to each point in space. If you imagine a region as a box, you would expect the number of possible field configurations to grow with the box's interior. Black holes suggest that this counting overestimates what gravity allows, because the ultimate storage capacity is set by the boundary. The Bekenstein bound and the Bekenstein, Hawking entropy become our guide rails, because they turn a mystery into a quantitative limit. For a black hole, S equals area divided by 4 times the Planck area, in units where constants are set, and the simplicity is part of the unease. The formula is easy to say, yet hard to accept, because it implies a radical compression of degrees of freedom. It suggests that the ultimate number of distinct states in a region is finite, and that the finiteness is geometric. To visualize this, imagine trying to store information by packing bits into a volume, like grains of sand filling a jar. Quantum field theory encourages that picture, because it treats space as a stage with infinitely many independent points. Black hole entropy says the jar has a different accounting system, where the maximum number of bits scales like the surface area of the jar, not the amount you can pour inside. If you try to exceed the bound, gravity responds by forming a horizon, and the horizon itself becomes the ledger. This is where the holographic principle enters as a disciplined conjecture rather than a casual metaphor. The physics inside a region might be fully described by degrees of freedom living on its boundary, with the interior emerging as an encoded description. The world could be like a hologram, where a lower dimensional pattern encodes a higher dimensional image, yet the image is still real. The principle is not that reality is fake, but that the bookkeeping of information is boundary limited. We keep the claim careful, because holography is not a slogan and not a mystical flourish. It is motivated by the entropy scaling that black holes force upon us, and it is enforced by dynamics rather than by taste. If you try to pack more information into a region than the area bound allows, gravity responds by forming a black hole, which hides the excess behind a horizon. The bound is enforced by collapse, not by convention, and that makes it feel like a law rather than an interpretation. At this point, a question hangs in the narration, because it is the kind of question that changes what space means. If the interior can be described by boundary data, then what is the interior, fundamentally? Is it a convenient emergent picture, like temperature emerging from molecular motion, or is it a basic ingredient that merely obeys a strange counting rule? When we say inside, are we naming a place, or are we naming a relationship between degrees of freedom? Now we step into the most concrete realization of holography, because the chapter needs an anchor that is more than philosophy. Anti-de Sitter space and conformal field theory provide that anchor, and they do it with a precision that surprised even experts. AD-CFT proposes an exact equivalence between a gravity theory and a bulk spacetime, and a quantum field theory without gravity on the boundary. It is not an analogy, but a duality, meaning both descriptions capture the same physics in different languages. In accessible terms, it says this, and the simplicity is part of its power. A universe with gravity in one higher dimension can be fully encoded by a quantum system living on its edge. The bulk geometry emerges from the boundary description, and bulk gravity dynamics correspond to boundary quantum dynamics. The two descriptions are different coordinate systems for the same underlying reality, and neither is more real than the other. To make the visual feel tangible, imagine a vast interior volume whose events cast no shadows outward, and then imagine that every event is nevertheless recoverable from patterns on the boundary. The boundary is not a physical wall, but a place where the theory can be defined cleanly, like the edge of a mathematical canvas. In ads, light rays can reach the boundary and return in finite time, which helps make the boundary a natural stage for encoding. The geometry itself cooperates with the idea of an edge-based description. We emphasize what AD-CFT is and what it is not, because the edge of the map invites exaggeration. It is not a proven model of our universe's cosmology, because our universe appears closer to de Sitter than anti-de Sitter, with accelerated expansion. It is not a direct observational claim, and it does not tell us that we live on a literal boundary. It is a proof of concept that holography can be exact, consistent, and calculable, which is already a profound shift. AD-CFT also changes what we mean by spacetime, because it suggests that geometry can be emergent rather than fundamental. If a boundary theory can encode a bulk, then distance, curvature, and even the existence of an interior can arise from quantum structure. In many discussions, the key structure is entanglement, the quantum correlation that links subsystems even when separated. The map might be built from correlations not drawn on a pre-existing stage, and the edge might be where the fundamental variables live. This loops back to the central question, because string theory helped make holography credible, technical, and hard to dismiss. D-branes and open strings gave a concrete way to build gauge theories on surfaces, with fields living where strings end. The same brane setups also produced black holes and curved spacetimes in the bulk description, sourced by the brane's energy and charge. Matching calculations from both sides made the duality feel less like poetry and more like engineering, because numbers agreed where they had no right to agree. In the string theory story, holography is not an optional interpretation layered on top of an otherwise complete framework. It is a structural consequence of how branes, gauge fields, and gravity fit together when you follow the mathematics to its end. The boundary theory is often a gauge theory that arises from open strings on branes, with symmetries that control its dynamics. The bulk gravity is described by closed strings in a curved background sourced by those branes, and the duality is a bridge built from the same ingredients. Now we return to finiteness with sharper teeth, because the information bound is not a decorative idea. If the information content of a region is bounded by area, then the number of distinct physical states in that region is finite, at least from the viewpoint of an observer restricted to that region. That does not automatically mean spacetime is a lattice, with little cubes of volume and a finite set of values at each cube, but it suggests that the continuum description contains redundancy, and that not every field configuration is physically independent once gravity is included. We ask the question without forcing an answer, because forcing an answer would be dishonest at this frontier. Does an entropy bound imply discreteness, like pixels at the Planck scale, where geometry has a smallest unit? Does it imply a computational limit, where the universe cannot represent arbitrary detail within a finite region? Or does it imply a different kind of continuity, where degrees of freedom remain continuous but are constrained by gravity's gauge redundancies and by the rules of horizon formation? Different approaches to quantum gravity respond differently, and the differences illuminate the same edge from different angles. Loop quantum gravity emphasizes discrete spectra for areas and volumes, suggesting a granular geometry where measurement outcomes come in quanta. String theory often keeps a smooth spacetime in calculations, yet introduces minimum lengths and dualities that limit localization and soften singular behavior. Holography suggests that the fundamental variables might not be geometric at all, and that geometry is a derived concept, like pressure in a fluid. We keep the tone mysterious, because the edge is not a single line, and it does not appear in only one domain. There is the cosmic horizon, which limits causal contact and confines our observations to a finite patch. There is the topological possibility, where space could be finite without a boundary, and where the map's edge is a loop. There is the quantum gravity limit, where localization creates horizons and makes small scales self-protecting. There is the holographic limit, where information scales with area and suggests a finite accounting. These limits also interact, and the interaction is where the chapter's unease deepens into something more structural. Horizons are not only observational barriers, like fog that blocks a distant view, but thermodynamic objects with entropy and temperature. Black hole horizons carry entropy, and in quantum theory they radiate, which makes them active participants in physics. Cosmological horizons in de Sitter space also have an associated temperature and entropy, suggesting that even empty accelerating space has a finite information content within its horizon. If our universe has a positive cosmological constant, then de Sitter-like behavior may persist into the far future, even as galaxies drift away. That would mean a future event horizon and a finite de Sitter entropy associated with our observable patch. The observable region would have a maximum number of states, even if space beyond exists and even if it is infinite. Reality could be finite from our perspective in a way that is not merely practical, but thermodynamic and fundamental. This is where the phrase finite space-time becomes more than geometry, because it becomes a statement about accessible degrees of freedom. Even if the global universe is infinite, the number of states that can ever affect us might be finite, because the horizon limits what can enter our causal domain. The edge could be a limit on history, not on distance, because it bounds the set of possible experiences and records. The map's border becomes a bound on what can be known, and perhaps on what can happen to us. We also connect this to the documentary's opening hook about an edge that is darker than the observable universe, because darkness can mean more than absence of light. The edge might be a rule about information, enforced by gravity, that prevents any observer from extracting unlimited detail. It might be that no observer can ever measure more than a certain amount of information about any region, because the act of extraction changes the region into a horizon. The universe would then be self-limiting, not by decree, but by the dynamics of space-time itself. Now we slow down and clarify what finiteness does not mean, because the mind reaches too quickly for the wrong picture. It does not mean we have found the universe's boundary in space, like a shell you could approach in a ship. It does not mean there is a final number we can write down for all of reality, as if the cosmos were a closed inventory. It means our best theories keep producing bounds, and those bounds keep pointing toward a finite accounting within any causal region. We also clarify what remains open, because the edge is visible as a silhouette, not as a measured wall. Cosmic topology is constrained but not determined, and the absence of repeats is informative but not decisive. Holography is exact in certain spacetimes, but its general form for cosmology is still being built, with de Sitter space remaining a harder case. The connection between entropy bounds and discreteness is suggestive, not settled, and the theories that hint at it do not yet converge on one final picture. The result is a kind of disciplined suspense, because the limits are real, and yet they do not close the story. We can measure curvature to high precision, yet topology can hide behind scales larger than our horizon. We can argue for minimum lengths, yet the operational meaning of those lengths depends on how measurement is defined in quantum gravity. We can compute black hole entropy, yet the microscopic states it counts are still a subject of deep investigation across frameworks. Now we pivot toward the next chapter's testing ground, because limits become sharpest where gravity is strongest and where horizons are unavoidable. Black holes are where horizons, entropy and information collide, and where the holographic accounting becomes more than a hint. Singularities are where space-time itself threatens to end, at least in classical relativity, and where quantum corrections must speak. The origin of the universe is where every limit we discussed might have been saturated, compressed into a beginning that is both a physical event and a conceptual boundary. The map's edge is no longer a distant boundary in space, and it is no longer only a subtle constraint in an equation. It is a boundary in description, where geometry, quantum theory and information are forced to agree or to break. If string theory is a serious candidate for unification, it must explain why these bounds exist and what lies behind them, if anything lies behind them at all. The next chapter follows the edge into the darkest laboratory we know, where the universe tests its own rules under extreme curvature. We end with the central question sharpened, not answered, because the edge is more compelling when it resists closure. If reality is bounded by horizons and by information, then finiteness is not a guess or a philosophical preference. It is a recurring pattern across cosmology, black holes and quantum gravity, appearing whenever we push our descriptions to their limits. The music of strings may be playing inside a finite score, and the final bar line might be written in entropy, waiting at the place where the map runs out. We enter the deepest night of the story, where gravity stops being gentle and geometry stops being trustworthy. Black holes and the Big Bang are not exotic side topics, because they sit exactly where our two rulebooks must either merge or confess their limits. In calmer regimes, general relativity treats spacetime as a smooth fabric, while quantum theory treats matter and fields as probabilistic and discrete in their outcomes. Here, in the extreme, those assumptions collide, and the collision is not metaphorical. It shows up as infinities, paradoxes, and boundaries that look physical but behave like bookkeeping devices. A black hole begins as an ordinary prediction of general relativity, almost disappointingly straightforward in its mathematics. Compress enough mass into a small enough region, and spacetime curves so steeply that even light cannot escape. The escape speed reaches the speed of light, and then surpasses it in the classical description. The result is an event horizon, a surface defined not by material strength, but by causal structure. The horizon is not a wall you hit. It is a boundary in the set of possible futures, separating what can still influence distant observers from what cannot. To picture it, imagine a spacetime diagram where light cones tilt as gravity strengthens. Far away, light cones stand upright, and future points forward in a familiar way. Closer in, the cones tip inward, subtly at first, then decisively, until every future-directed path points deeper toward the center. At the horizon, outward becomes as impossible as traveling backward in time. That is why the horizon is a causal boundary rather than a physical shell, and why it can exist even in empty space. Outside the horizon, classical spacetime still looks smooth and calculable, and that is part of the trap. Orbits, gravitational lensing, and time dilation follow the same equations that guide planets and GPS clocks, just pushed to stronger fields. A star can orbit a black hole, and its light can be bent into arcs and rings, producing images that look like cosmic mirages. Clocks near the hole tick more slowly relative to distant ones, and signals stretch redder as they climb out. Yet the horizon already hints at a new accounting, because it hides information from distant observers and forces physics to talk about what can be known. The outside description becomes strangely observer-dependent, not in what exists, but in what can be operationally recovered. Near the horizon, tidal forces can be mild or lethal depending on the black hole's mass, because what matters is the gradient of gravity across your body. For stellar black holes, those gradients can be violent, stretching and compressing matter into a long filament before it crosses. This is the famous spaghettification, and it is not science fiction. It is differential acceleration written into the curvature tensor. For supermassive black holes, the horizon can be so large that the local curvature at the crossing is comparatively gentle. In that case, an infalling observer might notice nothing special at the horizon, at least in classical theory. The drama is not in what you feel. The drama is in what the equations imply about causality, information, and the fate of predictions. Even the act of seeing the horizon depends on perspective, and this is where relativity turns cinematic. To a distant observer, an infalling object appears to slow, dim, and redden as it approaches the horizon. Its signals take longer and longer to arrive, and the light is stretched by gravitational redshift until it fades into darkness. To the infalling observer, the crossing happens in finite proper time, and the horizon is not marked by a flash or a shock. This mismatch is not a contradiction. It is a reminder that time is not universal, and that horizons are defined globally by the structure of space-time as a whole. Inside, classical relativity points toward a singularity where curvature diverges and the known laws lose their grip. Geodesics end in finite proper time, and the theory stops making predictions in the way a physical theory is supposed to. A singularity is not a discovered object sitting somewhere like a rock in space. It is a sign that the classical description has reached a boundary of validity, because the quantities it uses to describe reality become infinite or undefined. The singularity theorems of Penrose and Hawking sharpen this into a profound statement. Under broad conditions, collapse and cosmological expansion lead to incomplete paths in spacetime. In other words, classical spacetime cannot always be extended. That is why black holes are laboratories rather than monsters, even if their imagery invites fear. They concentrate energy, shrink operational length scales, and force horizons to appear with mathematical inevitability. They let us test whether spacetime is fundamental, or whether it is an emergent approximation that fails under extreme compression. They also let us test how quantum theory behaves when the background it assumes, smooth time and space, begins to wobble. Black holes are where the universe dares us to keep both rulebooks open at once. Now we tighten the stakes. because black holes are not only geometric traps, they behave like thermodynamic systems with temperature and entropy, and that claim rewires the meaning of a horizon. Thermodynamics is not optional physics, it is the accounting system of energy, disorder, and information. The second law, in particular, insists that total entropy does not decrease in a closed system. In the early 1970s, this created a crisis of consistency. If you throw a box of hot gas, full of entropy, into a black hole, the entropy seems to vanish from the outside world. The horizon looks like a shredder for the second law. Bekenstein argued that if entropy falls into a black hole, the outside world must not lose the second law, and the only way to save it is bold. The horizon itself must carry entropy, proportional to its area, so that the total entropy outside plus horizon never decreases. This was a radical move, because entropy usually counts microscopic states of matter, not states of empty geometry. Yet the logic was relentless. If black holes exist and thermodynamics is universal, then horizons must have an entropy budget. Hawking then made the argument quantitative using quantum fields on curved spacetime, and the result was even stranger. Black holes radiate, not because something leaks from the singularity, and not because the horizon is a hot surface in the ordinary sense. The radiation comes from the fact that particle is not an absolute concept in curved spacetime. What one observer calls vacuum, another can interpret as a bath of particles, because the definition of positive frequency depends on the geometry and the observer's motion. Hawking radiation is often pictured as particle pairs popping out of the vacuum near the horizon, and while that image is imperfect, it captures the tension. Quantum fluctuations constantly create correlated excitations, and near the horizon the strong gravitational field can separate those correlations. One part of the correlation can escape to infinity, while the other effectively falls inward, reducing the black hole's mass. The result is thermal radiation with a temperature set by surface gravity, a quantity that measures how strongly spacetime pulls at the horizon. The temperature is tiny for astrophysical black holes, far colder than the cosmic microwave background, which means they absorb more than they emit today. But the principle is decisive. A black hole is not perfectly black. Evaporation turns the horizon into a clock, and it gives the black hole a lifespan rather than an eternity. As mass decreases, temperature rises, and the final stages become more energetic. The classical picture of an eternal one-way boundary becomes a temporary phase, and the horizon becomes a dynamical object in the story. The black hole is no longer just a sink. It is a process, evolving through a sequence of states that must be described consistently by both gravity and quantum theory. Entropy completes the shock because it reveals what the horizon is really counting. The Bekenstein Hawking formula says entropy scales with horizon area, not interior volume. The number of states a black hole represents grows like area in Planck units, where the Planck length is the scale at which quantum gravity is expected to become unavoidable. That scaling is not a small detail. Ordinary matter has entropy that scales with volume because it has degrees of freedom throughout space. A black hole seems to compress the bookkeeping onto a surface, as if the interior is not where the information lives, or as if the interior is not an independent set of degrees of freedom at all. This is the same area scaling that Chapter 5 used to motivate holography, and here it becomes unavoidable. If the maximum entropy in a region scales like area, then the universe is hinting at a limit on information density. It is also hinting that locality, the idea that physics is built from independent points in space, may be only approximate. The horizon behaves like a ledger, and the area is the size of the ledger's page. Thermal radiation creates the central paradox, because thermality looks like amnesia. If the outgoing radiation is purely thermal, it carries no detailed memory of what fell in, only a temperature and a few macroscopic parameters. If the black hole evaporates completely, the initial pure quantum state seems to evolve into a mixed state, like a crisp quantum melody dissolving into static. That violates unitarity, the core rule that quantum probabilities must add up, and information must be preserved. It also threatens the predictability that makes quantum theory more than a statistical guess. The information paradox is not a philosophical complaint. It is a direct collision between quantum mechanics and classical spacetime, and it can be stated as a sharp inconsistency. Either information is lost, which would require modifying quantum theory, or something about horizons and locality is wrong, which would require modifying spacetime's classical picture, or our semi-classical calculation is incomplete, which would mean quantum gravity adds subtle correlations that restore unitarity. The paradox is the trial where quantum gravity must speak because the usual compromises fail. It also forces a question that sounds abstract but is physically concrete. Where is the information during evaporation, if the horizon hides the interior from the outside? Is it stored on the horizon in microscopic degrees of freedom, as the entropy suggests? Is it encoded non-locally in the radiation field, in correlations too delicate for semi-classical approximations to see? Or does the very notion of an inside break down when quantum effects are included? Each option reshapes what we mean by space, time, and causality. Now we step into string theory's first major courtroom victory, because it produced a statistical explanation of black hole entropy. In certain supersymmetric settings, string theory can count microstates, meaning it can identify the underlying quantum configurations that all look like the same black hole from far away. It can reproduce the Bekenstein, Hawking entropy from an underlying quantum system, not by analogy but by calculation. This mattered historically because it was one of the first times quantum gravity produced a controlled, numerical match to a gravitational result. The key construction uses d-branes, the non-perturbative objects that carry charges and host open strings. In string theory, strings can be open or closed, and open strings end on branes, giving branes a rich spectrum of excitations. D-branes are not just surfaces floating in space, they are dynamical objects with tension, charge, and quantum degrees of freedom. In the mid-1990s, Strominger and Waffer studied specific extremal and near-extremal black holes, chosen because supersymmetry stabilizes their properties and makes calculations tractable. They mapped the black hole to a bound state of d-branes and strings at weak coupling, where gravity is small and the system can be analyzed like a complicated but ordinary quantum many-body problem. They then did something deceptively simple in concept and brutally technical in execution. They counted the number of quantum states consistent with the charges, energy, and other conserved quantities, using tools from conformal field theory and supersymmetric index theorems. The degeneracy of states grows rapidly, and the logarithm of that degeneracy is the entropy. When they translated the result back into the strong coupling regime, where the same system becomes a black hole with a horizon, the entropy matched the area law. It matched not only the scaling but the precise numerical coefficient in regimes where the calculation is controlled. This was not a vague agreement. It was a rare moment where quantum gravity produced a number that classical geometry had already written down, and the two numbers clicked into place like gears. The horizon's entropy looked like ordinary statistical mechanics, not mystical bookkeeping. It suggested that the horizon is an emergent thermodynamic description of many microstates, the way temperature is an emergent description of many molecules. In that light, the black hole is not a single object. It is a coarse-grained label for an enormous family of quantum configurations. The success had limits that matter for honesty, and the documentary keeps the caution visible. The cleanest matches used highly symmetric black holes, often extremal and supersymmetric, where temperature can be very low and the system is protected from quantum corrections. Our astrophysical black holes are not protected by supersymmetry, and they form in messy collapse, surrounded by magnetic fields, turbulent plasma, and asymmetries. Still, the result changed the burden of proof. It showed that horizon entropy can come from microstates in a UV-complete theory, and it made the idea of black hole microphysics more than a slogan. It also reframed the meaning of the area law. If entropy counts microstates, and the microstates can be counted in a theory that has no fundamental horizon, then the horizon may be a thermodynamic feature rather than a fundamental boundary. That does not yet solve the information paradox, but it tells us the horizon is not a dead end for microscopic explanation. It is a signpost pointing toward deeper degrees of freedom. Now the narrative widens again, because counting microstates does not automatically solve the information paradox. A thermal spectrum still seems to erase details, and entropy alone does not tell you how information moves. The deeper question is where the information is stored during evaporation, and how it escapes without violating causality. If information comes out, it must come out in correlations among the Hawking quanta, correlations that are invisible if you only measure the average spectrum. The paradox is not about energy. It is about entanglement. In the semi-classical picture, each emitted Hawking quantum is entangled with a partner mode that falls inward. That entanglement grows with time, and if it keeps growing until the end, the radiation cannot be in a pure state. Yet unitarity demands that the full radiation, after complete evaporation, should be pure if the initial state was pure. This tension can be sharpened into inequalities, and it becomes a sharp contradiction when you assume three things at once: a smooth horizon, locality, and unitarity. Something must give. One string-inspired response is the fuzzball proposal, which attacks the assumption of a smooth universal interior. In this picture, the classical black hole with an empty interior and a singularity is an oversimplified average, like describing a gas as a featureless fluid while ignoring molecules. The true microstates are horizon-sized quantum configurations of strings and branes, each with its own geometry. There is no single smooth interior shared by all states, and there is no requirement that an infalling observer always sees vacuum at the horizon. A fuzzball replaces the classical singularity with structure, and it replaces the idea of a featureless horizon with a microstate-dependent region. The would-be horizon becomes a place where geometry depends on the specific quantum state, and the interior is not a universal vacuum. Radiation can then carry information, because it is emitted from a specific microstate rather than from a featureless horizon. The paradox is reframed as a mistake in assuming a smooth horizon for every state, when the true quantum description is more like a landscape of possibilities. Visually, this is a profound change. Instead of a single black silhouette with a clean boundary, we imagine a family of horizon-scale geometries, each one textured and distinct. Some are stringy throats, some are brain-bound configurations, and some are complicated topologies that would be smoothed away in a classical average. The black hole becomes less like a hole and more like a dense quantum object, with structure spread across the region where the horizon would have been. The darkness remains, but its meaning changes. Fuzzballs remain debated, and the documentary keeps the caution visible. The proposal is best developed for certain supersymmetric or near-supersymmetric cases, where explicit microstate geometries can be constructed. Extending it to realistic collapse, rotating astrophysical black holes and late-time evaporation is hard, both technically and conceptually. Yet it illustrates a key theme. Quantum gravity may resolve paradoxes by changing what we mean by spacetime inside the horizon, and by refusing to grant the classical interior the status of a universal stage. Another response comes from holography, where the information problem becomes a test of dual descriptions rather than a single picture. In ADS-CFT, a black hole in the bulk corresponds to a thermal state in a boundary quantum field theory. The boundary theory evolves unitarily by construction, because it is an ordinary quantum system with a well-defined Hamiltonian. If the duality is exact, information cannot be lost in the bulk either, even if the bulk description tempts us with a semi-classical story of loss. This does not instantly explain the mechanism in space-time terms, and that absence is itself instructive. It does something equally important. It proves that a consistent quantum theory with gravity can preserve information even when semi-classical reasoning suggests loss. The paradox becomes a clue that locality in the bulk is approximate, and that the horizon is not the whole story. The boundary description encodes the bulk in a way that is not point-by-point local, and that non-locality may be precisely what unitarity requires. Recent progress sharpened the point using quantum extremal surfaces and the page curve, and these ideas change the tone of the debate. The page curve is the expected entanglement pattern if evaporation is unitary. Entanglement entropy of the radiation rises at first, then turns over and falls as information emerges. Semi-classical calculations once predicted monotonic growth, implying information loss. New methods that include subtle gravitational contributions, including replica wormholes in the path integral, reproduce the page curve in controlled models. The results suggest that the semi-classical approximation was missing non-perturbative pieces of the entropy accounting, pieces that effectively allow the radiation to know about the interior in a way classical locality forbids. The striking part is not only the curve itself, it is the implication that the gravitational path integral can reorganize what counts as an independent region of spacetime. The island formula, in particular, tells us that the entropy of radiation can include contributions from regions inside the black hole, as if the interior becomes part of the radiation's entanglement wedge. That sounds like a trick until you remember what holography has been whispering all along. Spacetime regions may not be fundamental. They may be emergent partitions of quantum information. Now we pivot from black holes to the deeper singularity, because the universe itself seems to begin with one. The Big Bang in classical cosmology is not an explosion in space, with debris flying outward from a central point. It is a limit in time where densities and curvatures diverge when we run equations backward, and where the scale factor of the universe shrinks towards zero. Every location in space participates, because space itself is what is expanding. The singularity is not somewhere, it is somewhen, a boundary of the classical timeline. In standard general relativity with reasonable energy conditions, singularity theorems imply past incompleteness, and the result is conceptually similar to black hole collapse. The message is not that a point of infinite density literally existed as a physical object. The message is that the classical spacetime description cannot be extended indefinitely into the past, at least not without new physics. The beginning might be real, or it might be the edge of a map, a place where the coordinates and equations we trust stop being meaningful. Historically, this was not merely a mathematical curiosity. Early cosmology wrestled with whether the universe had a beginning or was eternal, and the discovery of cosmic expansion turned that philosophical question into physics. The cosmic microwave background later provided a fossil image of the hot early universe, and nucleosynthesis tied the early thermal history to observed light element abundances. Yet none of those successes reach all the way to the singularity. They validate the hot Big Bang as an early phase, not necessarily as an absolute beginning. Quantum gravity offers possible alternatives, and we present them carefully as scenarios rather than established history. One family is pre-Big Bang models inspired by string theory, where a contracting phase precedes the hot expansion. In these pictures, stringy symmetries and dualities can relate small and large scales, suggesting that what looks like a singular beginning in one description may be a transition in another. Another family is ekpyrotic and cyclic ideas, often framed in brain cosmology. In those, a hot Big Bang can be triggered by a brain collision in a higher dimensional bulk, turning the beginning into an event in a larger spacetime. Bounce cosmologies offer a third possibility, where contraction transitions to expansion without a singularity. The bounce can be driven by quantum gravitational effects, modified matter content, or effective corrections to Einstein's equations. The central hope is simple to state. When densities approach the Planck scale, quantum effects generate a repulsive contribution that prevents infinite curvature. Yet the details are unforgiving. Each approach must confront stability, entropy growth, and the generation of the observed perturbations. None is yet a settled replacement for the standard picture, and the documentary treats them as active hypotheses rather than established chapters of history. These scenarios also face a subtle thermodynamic challenge. If the universe cycles or bounces repeatedly, what happens to entropy from one cycle to the next? Does it accumulate, making each cycle larger and longer, or is there a mechanism that resets the bookkeeping? Even asking the question reveals how deeply thermodynamics is woven into cosmology. The universe is not only geometry, it is an evolving statistical system. Now we slow down and separate what we can infer from what we can only imagine. The earliest directly constrained epoch is not the Planck era. It is the era when inflation or some alternative mechanism imprinted primordial perturbations that later became galaxies. The cosmic microwave background is a snapshot of the universe when it was about 380,000 years old, but its tiny temperature variations carry information from much earlier. Those variations are a map of primordial quantum fluctuations, stretched to cosmic scales and then frozen into the plasma. Inflation is supported by the near-scale invariant spectrum of temperature fluctuations in the cosmic microwave background, and by the pattern of acoustic peaks that match a simple early universe story. Quantum fluctuations stretched to cosmic scales provide a mechanism for structure, turning microscopic uncertainty into macroscopic pattern. Yet inflation is not a complete theory of the beginning. It is an effective description that likely sits below the Planck scale, and it may hide earlier physics behind exponential expansion. In many models, inflation acts like a cosmic eraser, smoothing away prior curvature and diluting relics, which is both a feature and a limitation. Primordial gravitational waves would be a sharper probe, because they would carry information about the energy scale of inflation and about the dynamics of the early expansion. Their imprint would appear as B-mode polarization patterns in the CMB, a faint swirling signature in the polarization field. Detection would constrain early universe dynamics and could rule out large classes of models. Non-detection also constrains, and it already pushes many simple inflationary potentials into tension. The absence of a signal is not silence. It is a boundary drawn around what the early universe could have been. Even with perfect measurements, the Planck era remains uncertain, because the very language of space-time may fail there. At times, near 10 Ra 43 seconds, quantum fluctuations of geometry itself should matter, and the separation between background and field becomes questionable. Our usual notions of time, distance, and particle may not apply, because those notions assume a stable stage on which events occur. The best we can do is infer indirectly, using consistency with later observables and with the internal demands of quantum gravity. We can ask what a viable theory must reduce to when the universe cools and expands, and we can test whether it can reproduce the patterns we actually see. Now we return to the chapter's central tension, because it is the climax of the documentary's question. Do black holes and the Big Bang reveal a true limit in reality, or only a limit in our description? Is there a beginning because time is finite, or because classical time is an emergent coordinate that fails? The question sounds metaphysical until you remember that singularities and paradoxes are not opinions. They are mathematical alarms ringing inside our best theories. If time is fundamental, then a beginning is a boundary condition the universe must accept, and the question becomes, why that condition, and why that particular low-entropy start? We can ask whether the boundary is unique, whether it could have been different, and what selects it. If time is emergent, then the question changes form, because emergent variables can have edges without implying a literal first moment. The beginning could be like the edge of temperature at absolute zero, a limit of a macroscopic variable rather than a point you can physically inhabit. The universe might not start so much as enter the regime where time becomes a useful description. Holography and entanglement suggest a route to emergence, and they do so with surprising mathematical precision. In many models, space-time connectivity is tied to patterns of quantum entanglement, and geometry can be reconstructed from entanglement entropy and correlation structure, at least in special settings. In ADS-CFT, for example, bulk distances relate to boundary correlations, and the growth of entanglement can be associated with the growth of geometric regions. The idea is not that entanglement is a substance that fills space. The idea is that entanglement is part of the code that defines what space even means. This idea links black holes to cosmology through the same principle. If space-time emerges from quantum information, then singularities may be artifacts of forcing emergent variables beyond their domain, like demanding a fluid description at the scale of individual molecules. The breakdown at a singularity would then be like the breakdown of Navier, Stokes equations at atomic scales. The cure would not be a patch to geometry. The cure would be the underlying quantum description, where the degrees of freedom are not points in space but something more abstract and more fundamental. String theory enters here as a candidate for that underlying description, but it does not yet deliver a final cosmological narrative. It offers tools that soften ultraviolet behavior because strings smear interactions over a finite length, rather than concentrating them at a point. It offers dualities that blur small and large, suggesting that what looks like a catastrophic compression may have an equivalent non-singular description. It offers holographic examples where gravity emerges from non-gravitational degrees of freedom, turning space-time into a derived concept. It also offers concrete microstate counting that turns horizon entropy into statistical mechanics. These are not final answers, they are constraints on what answers can be. Now we build the chapter's final rise, because the extremes force a single question. If reality has an edge, black holes and beginnings are where it should reveal itself, because they push every concept to its breaking point. The edge might be a maximum information density, enforced by horizon formation and the area law. The edge might be a minimum operational length, enforced by stringy extension and duality. The edge might be a limit of classical time, enforced by quantum gravity when the universe is too young for space-time to behave classically. Yet the climax is not only conceptual, it is methodological, because a theory that lives at the edge risks becoming hard to test, and physics cannot survive on elegance alone. String theory and quantum gravity can be internally consistent and still be wrong about nature. A beautiful framework can be a map of a world that does not exist. The documentary cannot end this chapter by claiming victory, because the evidence is partial and the terrain is extreme. It must end by turning the tension into the next problem, and by admitting that the hardest part may be connecting deep principles to measurable consequences, Now we transition from confronting extremes to asking the hardest question of all. How do we test these ideas without direct access to Planck energies, and without waiting for an evaporating black hole that lasts longer than the age of the universe? What would count as evidence that spacetime is emergent, that information is never lost, and that singularities are resolved? And what would count as a decisive refutation, rather than another adjustable interpretation? We can look for indirect signatures, and the modern era is finally rich in them. Precision measurements of black hole mergers test horizon dynamics and ring-down spectra, and they can reveal deviations from classical predictions. The ring-down is not just a fading sound. It is a spectrum of quasi-normal modes, shaped by the black hole's mass and spin, and sensitive to whether the object has a true horizon or some exotic near-horizon structure. Observations of accretion and shadows probe strong field geometry, though they do not yet resolve quantum structure. Still, every sharper image and every cleaner waveform trims the space of possibilities. Cosmological surveys test primordial statistics, non-Gaussianity, and the presence of relics like cosmic strings, which are not guaranteed but are allowed in some high-energy scenarios. Large-scale structure maps the distribution of matter across billions of light-years, and it carries a memory of the early universe's initial conditions. Subtle deviations from Gaussian randomness could point to specific inflationary dynamics or to alternatives. Even null results matter because they restrict which early universe mechanisms remain plausible. We can also test internal consistency, which is not a substitute for data but is still a filter that physics has always used. Holography provides non-perturbative definitions in certain spacetimes, and it can expose hidden contradictions in naive semi-classical reasoning. Microstate counting provides statistical matches that any candidate theory must reproduce, because the area law is not negotiable once black hole thermodynamics is accepted. Unitarity and causality constrain what modifications to locality are allowed, because not every fix to the paradox is compatible with the rest of physics. The space of plausible quantum gravities is narrower than it looks, and it becomes narrower as the constraints accumulate. The chapter ends with the central question sharpened to its most uncomfortable form. If string theory is a serious candidate for unification, it implies that spacetime may be secondary, built from deeper quantum structure. It implies that horizons are not merely boundaries in space, but accounting surfaces for information, where entropy measures hidden microstates. It implies that the universe may be finite in what it can store and reveal, even if it is vast in size, and it implies that our most reliable intuitions about inside and outside, about before and after, may be approximations that fail at the edge. We return quietly to the opening hook's darker possibility. The universe might be made of music, but the score may have a last measure, and the last measure may be written in the language of quantum information. Black holes and the Big Bang are where the ink runs thickest, where equations become warnings, and where the page may end or turn into a different kind of book. In the next chapter, we step back from the abyss and ask what it would mean to accept a theory of everything that resists direct verification, and what kind of evidence could still make it science. We began with a 1968 mathematical accident that sounded like music in equations, and we end by asking what that music can prove about the world. Back then, the Veneziano amplitude was a clever fit to scattering data, yet it hinted at an underlying spectrum, like harmonics emerging from a single instrument. A unified theory would unify forces and particles in one consistent framework, so the same principles explain photons, quarks, and the fields that bind them. It would also unify quantum mechanics with gravity, so spacetime and probability stop contradicting when the universe is pushed to extremes. In the standard model, forces are gauge fields, and matter comes in families with repeating patterns of charge and mass. The mathematics is precise but compartmentalized. 3-gauge interactions, a separate Higgs mechanism, and parameters that must be measured rather than derived. In general relativity, gravity is geometry, and energy tells spacetime how to curve. The picture is visual and continuous. Matter drags on the metric, light bends along geodesics, and clocks tick differently depending on gravitational potential. The conflict appears when quantum uncertainty meets dynamical spacetime at extreme density, where even the background becomes a fluctuating participant. At the Planck scale, point particles drive infinities, and horizons threaten measurement itself, because concentrating energy to probe smaller distances can collapse the region you are trying to examine. String theory offered a different starting point, with extended objects replacing points and softening the ultraviolet violence of collisions. A string cannot strike with perfect localization. Its finite length smears interactions, and that smearing changes the bookkeeping of quantum loops. The same quantization that yields gauge bosons also yields a massless spin 2 graviton, the exact quantum signature of a gravitational field. That graviton is not inserted by hand, and that is the theory's central promise, because the demand for consistency forces gravity to appear. Quantum gravity emerges as a required vibration, and low energy limits resemble Einstein's equations with calculable corrections. Those corrections are usually tiny, yet they matter conceptually, because they show how classical curvature can arise from quantum excitations. String consistency also demanded extra dimensions, supersymmetry in many versions, and a web of dualities that connect seemingly different theories. Those constraints felt like clues that the framework is deeper than any single approximation, as if multiple maps were projections of one hidden terrain. Now we tighten the stakes, because a theory of everything must face evidence. A beautiful map is not enough if it cannot be checked against the sky, and physics ultimately answers to nature's data, not our preferences. The testability problem begins with energy, because quantum gravity becomes unavoidable only when energies approach the Planck scale. Planck energies are around 1019 GeV, far beyond any collider we can plausibly build, and far beyond what earthbound magnets can steer. To probe 10 or 35 meters directly, you would need collisions so energetic they risk making black holes, turning the experiment into its own obstruction. Nature may hide the smallest scales behind the very gravity we're trying to quantize, an ironic kind of censorship built into spacetime. Direct tests are still meaningful, but they target lower energy consequences, where new physics could leak into measurable regimes. Colliders can search for new particles, and tabletop experiments can test gravity at sub-millimeter ranges, where extra forces might still be hiding. Short-range gravity tests look for deviations from the inverse square law, using torsion balances, microcantilevers, and exquisitely controlled systematics. Extra dimensions could leak gravitational flux, changing how force falls with distance, so gravity would weaken faster than Newton's simple prediction. Colliders look for missing energy, resonances, or Kaluza-Klein towers, which would appear as repeated heavy states with regular spacing. If extra dimensions are large enough, new modes could appear as heavy copies of known fields, briefly flashing into existence before decaying into familiar particles. So far, the Large Hadron Collider has not found clear deviations from the standard model, despite pushing into multi-TV territory with enormous datasets. The absence pushes many simple models upward in scale and reduces their naturalness appeal, because the easy signatures have not appeared. Supersymmetry sits at the center of this tension, partly because it once looked like a Swiss Army knife for theoretical problems. It promised a stabilizing symmetry, gauge coupling unification, and a dark matter candidate, while also improving the quantum behavior of gravity in supersymmetric string constructions. Experiments have not found superpartners at the energies first expected, and the clean missing energy patterns have not materialized. That does not kill supersymmetry, but it forces it to be heavier, more hidden, or more subtle, with decay chains that evade simple triggers. Heavier superpartners weaken the original naturalness argument, because the Higgs mass then requires more delicate cancellations. They also shift attention to split spectra, compressed decays, and scenarios where signatures are hard to isolate, especially when backgrounds mimic the signal too well. Now we step from direct test to indirect signatures, because cosmology can amplify tiny physics. The early universe can act like an accelerator that ran once, leaving fossils in radiation, and it can preserve patterns that no laboratory could ever reproduce. One window is primordial gravitational waves, ripples in space-time generated by violent early dynamics, and then stretched across the cosmos. They would encode the energy scale and dynamics of inflation, or any alternative early phase, and they would arrive today as a faint, persistent hum. In the CMB, those waves could appear as B-mode polarization patterns, a subtle twisting of microwave light across the sky. A detection would constrain high-energy physics, and a non-detection already rules out broad classes, because it limits how much tensor power the early universe could have produced. Another window is cosmic strings, which are astrophysical relics of symmetry breaking, like cracks forming as a hot universe cools. They are distinct from fundamental strings, but they can arise in string-motivated scenarios, especially when branes and fields reorganize during the universe's phase transitions. Cosmic strings would lens light in characteristic ways, producing double images without the usual distortion of a galaxy lens. They would also generate gravitational wave backgrounds, and pulsar timing arrays, interferometers, and lensing surveys can constrain their tension with steadily improving sensitivity. CMB anomalies are a softer clue, and they demand caution, because human pattern finding is powerful and sometimes misleading. Large angle alignments, hemispherical asymmetry, or unusual cold spots could be statistics, systematics, or new physics, and the challenge is to separate a real signal from a cosmic coincidence. Extra dimensions could also leave imprints through modified expansion histories or altered particle production, subtly changing how energy density evolves. Any such claim must survive degeneracies with ordinary cosmological parameters, because a tweak in geometry can masquerade as a tweak in matter content. Another possible signature is a deviation from the inverse square law at short distances, where new light fields or geometric effects might appear. That would not prove strings, but it would point toward new gravitational degrees of freedom, and it would reshape how we think about spacetime's hidden structure. We also watch for hints in high-precision measurements of gravity in quantum systems, where tiny discrepancies can accumulate into meaning. Tiny violations of equivalence, Lorentz symmetry, or standard dispersion relations would be revolutionary, because they would show that the foundational symmetries of modern physics are only approximate. Yet most string-scale effects are expected to be extremely small if the fundamental scale is high, and many compactifications hide new physics behind enormous energy gaps. The theory may be right and still be quiet in every experiment we can run, which is a sobering possibility for any empirical program. Now we return to what counts as evidence, because cosmology often works without laboratory control. We infer the early universe from patterns that survived billions of years of evolution, and we test hypotheses by demanding consistency across many independent datasets. Evidence can be a direct detection, like a new particle, or a consistent set of correlated signatures that line up across instruments. It can also be the absence of signals, which trims parameter space and forces sharper predictions, turning nothing found into a quantitative constraint. The danger is that a flexible framework can fit almost anything after the fact, especially when there are many adjustable ingredients. If a theory can accommodate every outcome, it risks becoming a language for possibility, rather than a claim about reality, and that is a real methodological worry. String theory's defenders answer with a different standard of progress, emphasizing that not every mathematically allowed idea is physically consistent. They point to internal consistency, anomaly cancellation, dualities, and the way gravity and gauge theory interlock, arguing that these are non-trivial filters on what a universe can be. Mathematics can be a guide when experiments are distant, because consistency can rule out vast regions of idea space. Dualities can reveal that different pictures describe one structure, so what looked like separate theories become different coordinate systems on the same underlying object. Adson-CFT duality is the clearest example of that structure, and it arrived as a shock in the late 1990s. It shows that a quantum theory without gravity can encode a higher dimensional spacetime with gravity, as if the boundary's degrees of freedom secretly contain the bulk's geometry. That result suggests spacetime can be emergent, built from entanglement and information rather than assumed as a stage. It also suggests that locality may be approximate, not fundamental, because distant points in the bulk can correspond to subtle, distributed correlations on the boundary. But mathematics can also seduce, and beauty can overfit, especially when observational anchors are scarce. A consistent framework can still describe a universe that is not ours, so the hard question remains: which mathematical necessities are truly physical necessities? Now we revisit finiteness, because the documentary's darker possibility was never only about size. Finiteness can mean finite volume, finite information, or finite resolution, and each meaning changes what it would take to know the whole story. A universe can be finite in topology without an edge, because space can wrap around itself through global identifications. Curvature and identification can close space like a loop, even if local geometry looks flat. So a traveller could, in principle, return without ever meeting a boundary. Observations constrain curvature to be near zero, using the CMB's acoustic peaks and the geometry of large-scale structure. Searches for repeating patterns have found no decisive matches, which leaves compact topologies possible, but likely larger than our horizon, and therefore hidden from direct confirmation. Finiteness can also mean finite information in a causal patch, where horizons limit what can ever be observed. Horizons carry entropy, and black hole thermodynamics suggest a maximum number of state scales with area, implying that nature counts information in a surprisingly geometric way. Holography turns that scaling into a principle, and it reframes what inside a region even means. The degrees of freedom describing a region may live on a boundary, with the interior emerging as an encoded description, real in practice, yet constrained by an information budget. Finiteness can also mean finite resolution at the Planck scale, where the notion of a sharply defined point may fail. Attempts to probe smaller distances may create horizons, and string dualities blur the meaning of smaller versus larger, because a very small circle can be physically equivalent to a large one. These are different senses of finiteness, and they do not automatically imply a final wall. The universe could be bounded in what can be known without being bounded by a physical border, and that distinction matters when we talk about ultimate explanations. Now we answer the central question carefully, because the honest answer is layered. String theory suggests spacetime may be emergent, extra dimensions may be real but hidden, and limits may be fundamental, even when the everyday world looks smooth and continuous. It also suggests the universe can be finite in multiple ways, without having an edge you can reach, like a coastline that never appears because you're always at sea. The edge can be a horizon, a topology, or an information bound, and each edge is as much about observers as it is about geometry. What we cannot yet say is whether string theory is the unique correct unification, or one consistent member of a larger set. We also cannot yet say which compactification, which vacuum, or which cosmological history nature chose, because the data do not yet point decisively to one branch. What we can say is that the framework changed the meaning of unification even before it was confirmed by experiment. It linked particles to geometry, forced gravity into quantum theory, and made information a physical constraint, so the old separation between stuff and space became harder to defend. Now we transition from theory to the near future, because the next decade will still test the edges. Gravitational wave astronomy will map strong gravity and search for primordial backgrounds, while also checking whether black hole mergers behave exactly as general relativity predicts. CMB polarization experiments will push B-mode sensitivity and tighten early universe bounds, reducing the room for high-energy scenarios. Large-scale surveys will refine primordial statistics and hunt for relics like cosmic strings, using billions of galaxies as a cosmic detector array. Particle physics will keep squeezing supersymmetry in extra-dimension scenarios, not only through higher energies but through better analyses and rarer channels. Tabletop gravity will keep testing the inverse square law in new light fields, where careful engineering can sometimes outperform sheer energy. Even null results will matter, because they force the theory to be more specific, and they punish overly simple stories. They also clarify which questions are physics today and which remain philosophy, at least until technology shifts what is measurable. The philosophical weight is not an escape from science, but a consequence of its limits, and physics has faced such limits before. If reality has a finite information budget, then complete description may be impossible for any observer, even in principle, and that possibility should change how we talk about final answers. Yet the drive to map the whole story persists, even when the map cannot be finished, because curiosity is not conditional on closure. The 1968 clue still echoes, because it taught physics to listen for hidden structure, patterns that are not obvious until you translate them into the right language. In the end, the universe can be imagined as a quiet instrument, suspended in darkness and vibrating with rules we only partly hear. Strings and brains are possible notes, horizons and boundaries are possible measures, and information is the rhythm, keeping the score honest. We may never touch the Planck scale directly, but we can still hear constraints in the harmonics, the way a musician hears tension in a chord. Every observation is a partial chord, and every theory is an attempt to resolve it, without losing the subtle dissonances that make it real. If reality is finite, it may be finite without an edge, and limited without being small, like a book with a fixed number of pages but endless interpretations. The mystery is not that the story ends, but that it keeps inviting us to read further, even as the last chapter stays just out of reach. We close where we began, with music hidden beneath matter and space-time, and with equations that behave like instruments. The last notes may live at the limits of reality, and the listening may be endless because the universe does not promise completion, only deeper hearing. We began at the widest boundary we can see, the cosmic horizon, and followed the trail inward to the smaller scales. Along that descent, the universe kept repeating the same lesson, that observation is always framed by limits, like cones, expansion, uncertainty, and the strange bookkeeping of entropy. At the Planck length, where our two best rulebooks collide, point particles turn pathological, and the mathematics that once only fit hadrons starts to look like a map. Veneziano's 1968 accident was not just a clever curve through scattering data. It was a doorway into duality, an infinite tower of states, and the idea that interactions are smoother when the actors are extended. Strings replace sharp vertices with world sheets, and in doing so they don't merely tolerate gravity, they generate it, because a massless spin-2 mode appears as a requirement rather than an option. The cost of that elegance is hidden architecture, extra dimensions curled into shapes that decide which particles exist, how forces run, and whether our constants are stable or drifting. Dualities then pull the rug from under our intuitions about size and substance, telling us that a small circle can be the same as a large one, and that fundamental depends on where you stand. In that deeper picture, brains join strings, an 11th dimension can emerge, and what looked like 5 competing theories becomes one connected landscape of descriptions. Yet the closer we came to edges, black hole horizons, cosmological event horizons, and the operational limit of localization, the more the story shifted from geometry to information. Black holes radiate, entropy scales with area, and holography whispers that the bulk of space may be encoded on a boundary, as if reality is less a volume and more a ledger. The information paradox, the page curve, and the recent language of islands and quantum extremal surfaces suggest that space-time itself may be a coarse-grained story told by entanglement, not an irreducible stage beneath it. That possibility reframes finiteness, not as a wall at the end of space, but as a bound on resolution, on storage, and on what any observer can ever reconstruct. And when we asked how such a grand framework could be tested, the answer was both sobering and hopeful, because accelerators may never reach the Planck scale, but the early universe might have already run the experiment for us. Primordial gravitational waves, cosmic strings, subtle departures in the CMB, and short-range test of gravity become the quiet places where extra dimensions, high-energy corrections, or new symmetries might leave fingerprints. Still, the landscape problem remains, because many compactifications can imitate the same low-energy world, and without a selection principle, explaining everything risks meaning accommodating anything. So the documentary's revelations converge on a tension that is not yet resolved. That quantum mechanics and general relativity are each astonishingly right, yet together they point toward a deeper language where distance, time, and even locality may be approximate. In that language, finiteness is not merely about whether the universe wraps around like a torus or curves like a sphere. It is about whether reality enforces a smallest meaningful question we can ask. What we have for now is a set of clues that rhyme across chapters: duality and scattering, duality and geometry, horizons that behave like thermodynamic systems, and a universe that seems to protect itself from infinite scrutiny. Taken together, they suggest that the deeper structure of space-time may be less like empty continuity and more like a structured tapestry, woven from vibrations, constraints, and counted bits. Yet the tapestry is not fully in view, and the threads we tug sometimes lead to new knots, new paradoxes, and new forms of ignorance that look, strangely, like progress. That is the earned ending of our journey, not a final theorem, but a coherent suspicion that the universe is simultaneously more constrained than our classical imagination, and more inventive than our equations have yet allowed. What then was space-time really made of, and were we about to find an edge we can't cross? If string theory is pointing in the right direction, the edge is not a cliff at the end of the cosmos, but a principle, a minimum effective length, and a maximum information density enforced by quantum gravity. The equations that started to sing in 1968 may be telling us that reality is finite in resolution, and that below a certain scale, asking for a sharper picture does not reveal more detail. It changes the question into a horizon. In that sense, the universe may be bounded without being boxed in, and finite without being small, because topology can close space without giving it a border, and holography can limit content without limiting wonder. But the opening question also deserves a humbler reframing, because even if strings are real, they may be one dialect of a deeper grammar, and what is fundamental may depend on which description makes the paradox dissolve. So the most honest answer is that we are not yet sure where the edge lies, only that every time we push toward it, physics answers with a new kind of bookkeeping. The limit may be a smallest length, a boundary of information, or an emergent notion that only appears when we insist on viewing the world as made of points. And if that is true, then the deepest structure of space-time is not simply hidden, it is relational, defined by what can be measured, encoded, and consistently described. The universe may not be an infinite stage beneath actors, but a script written in constraints, where consistency forces new dimensions and paradox forces new principles. Whether string theory is uniquely selected, or one member of a family remains open, but the direction of travel is clear, toward a cosmos where geometry and quantum theory are not rivals, but two shadows cast by the same underlying light. If there is a final thought worth carrying into the dark, it is this: that the edge we fear may also be the seam that holds reality together. A finite tapestry can still be endless to explore, because what matters is not the size of the stage, but the depth of the pattern, and the pattern keeps unfolding whenever we learn how to listen. If you want to stay with the mystery, follow the evidence as it arrives, in new sky surveys, new gravitational wave maps, and the next quiet mathematical accident that makes the equations sing. What, then, was space-time really made of, and were we about to find an edge we can't cross? If string theory is pointing in the right direction, the edge is not a cliff at the end of the cosmos, but a principle, a minimum effective length, and a maximum information density enforced by quantum gravity. The equations that started to sing in 1968 may be telling us that reality is finite in resolution, and that below a certain scale, asking for a sharper picture does not reveal more detail, it changes the question into a horizon. In that sense, the universe may be bounded without being boxed in, and finite without being small, because topology can close space without giving it a border, and holography can limit content without limiting wonder. But the opening question also deserves a humbler reframing, because even if strings are real, they may be one dialect of a deeper grammar, and what is fundamental may depend on which description makes the paradox dissolve. So the most honest answer is that we're not yet sure where the edge lies, only that every time we push toward it, physics answers with a new kind of bookkeeping. If there is a final thought worth carrying into the dark, it is this: that the edge we fear may also be the seam that holds reality together. A finite tapestry can still be endless to explore, because what matters is not the size of the stage, but the depth of the pattern, and the pattern keeps unfolding whenever we learn how to listen. If you want to stay with the mystery, follow the evidence as it arrives, in new sky surveys, new gravitational wave maps, and the next quiet mathematical accident that makes the equations sing.